Imagine you could tune the very fabric of reality with the same confidence you choose a song to lift your spirit. What if the empty space that surrounds you is not a void at all, but a humming sea of possibilities waiting for your intention to set it in motion? In the next few minutes, you will travel deep into the quantum realm, where every whisper of energy, every flicker of a field, is a reminder that you hold the power to shape outcomes that once seemed fixed. You will discover how the hidden rhythm of vacuum fluctuations, the gentle push of the Casimir force, and the warm glow that appears when you accelerate can become sources of inspiration, tools for decisive action, and symbols of the unstoppable potential inside you. By the end of this journey, you will feel a surge of clarity, a fresh sense of agency, and a concrete plan to bring the quantum mindset into every challenge you face today. Let us begin by opening the door to a world most people call empty. Picture the night sky not as a black canvas, but as a vast ocean of invisible fields that stretch through every corner of existence. Light, electrons, the forces that bind atoms, each of these is a ripple on a deeper sea, a wave that never truly settles. Even when a field is in what physicists call its ground state, it does not lie still. It quivers like a heart monitor that never reaches zero, a perpetual tremor that is the lowest energy the universe permits. In quantum language, the word minimum does not mean nothing. It means the smallest amount you can have without breaking the rules. This subtle shift in meaning is the first key that unlocks your own potential. The baseline you think is a limitation is actually a springboard for creative motion. Take a deep breath and feel the mattress supporting you. As you exhale, imagine that support is not a static slab, but a field of countless tiny vibrations, each one a quantum of zero-point energy. Those vibrations are the reason a perfectly empty vacuum still hums with a soft hiss that never disappears. If you could turn down the universe's volume to absolute silence, you would still hear that hiss, a reminder that even the quietest background carries a ledger of borrowed energy that always balances. This is not poetic fluff, it is a precise statement of how the quantum world keeps its accounts. Every fluctuation that appears for an instant is matched by an opposite one, so the total sum remains zero, but the momentary activity is real, measurable, and, most importantly, exploitable. Now picture yourself as a scientist standing before two perfectly smooth mirrors, placed a hair's breadth apart in that same sea of fields. No particles, no light, no heat, just the mirrors and the space between them. Classical intuition tells you that nothing should happen. Quantum reality, however, says that the space between the mirrors can only support certain standing waves, just as a violin string can only vibrate at specific notes. Outside the gap, the field enjoys a richer spectrum of possible vibrations inside. The spectrum is trimmed by the geometry of the mirrors. The imbalance creates a net pressure that pushes the mirrors together. This is the Casimir effect, a force born not from any material substance, but from the way empty space is shaped. It is a perfect illustration of a principle you can carry into your life. The boundaries you set, the structures you create, determine which possibilities are allowed and which are suppressed. By designing your environment with intention, you can generate forces that move you forward, even when the surrounding world seems inert. Feel the excitement building as you realize that the same mathematics that predicts the pull of two mirrors also predicts the gentle warmth you would feel if you accelerated through empty space. This is the Unruh effect. Imagine you are strapped into a rocket that fires with a steady, unrelenting thrust, cutting through a universe that, to a stationary observer, is perfectly cold and dark. Your thermometer, however, begins to click as though you are immersed in a warm fog, its temperature rising in direct proportion to the acceleration you experience. No new particles are being conjured from nothing, rather. The definition of what counts as a particle changes with your state of motion. From your accelerated perspective, the quantum fields appear as a thermal bath. This tells you a profound lesson: the reality you perceive is shaped by how you move through it. Change your velocity, change your perception, and you can turn a seemingly barren situation into a source of heat, energy, and opportunity. All of these phenomena share a common thread. They arise from the interplay between fields, the limits imposed by geometry, and the observer's motion. In each case, the quantum world does not break its own rules, it follows them with a precision that can feel magical to the untrained eye. The magic, however, is a disciplined dance of possibilities, and you can learn the steps. When you feel stuck, ask yourself what boundary conditions you have unknowingly set. Are you limiting the spectrum of ideas that can resonate in your mind? Are you holding onto a geometry of thought that only permits a narrow set of solutions? By reshaping those conditions, be opening a new perspective. By changing the distance between you and a problem, you allow fresh modes to appear, and the resulting pressure can propel you toward breakthrough. Let us turn this insight into immediate action. First, identify a current challenge that feels like a dead end. Visualize the problem as two plates, one representing the obstacle and the other representing your goal, with a thin gap of uncertainty between them. Now ask what field is present in that gap. Is it fear, doubt, or perhaps a lack of information? Next, deliberately alter the geometry of the gap. This could mean gathering new data, seeking a fresh mentor, or simply changing the time of day you work on the issue. Each adjustment changes the allowed vibrational modes in the quantum analogy, and the Casimir pressure will shift accordingly. You may feel a subtle pull toward a solution that was previously invisible. Trust that pull, because it is the quantum field rewarding your intentional reshaping of the environment. Second, harness the principle of acceleration-induced warmth. In your daily routine, create moments of sustained, purposeful acceleration. Intense focus on a single task for a defined period, free from distraction. As you maintain that forward thrust, notice the internal warmth of engagement, the rise in mental temperature that fuels creativity. This is not a metaphor, it mirrors the Unruh effect, where steady acceleration translates into a thermal sensation. By committing to regular bursts of deep work, you generate a personal heat that can melt the ice of procrastination and inertia. Third, remember that zero-point energy is always present, even when you feel empty. The baseline hum of the universe is a reminder that you are never truly without resources. When anxiety whispers that you lack motivation, picture the vacuum's jitter as a background drumbeat you can tap into. Align your actions with that rhythm, and you will find a steady undercurrent of energy that supports even the smallest steps. This is the quantum mindset, acknowledging the ever-present baseline and using it as a foundation rather than a limitation. Now, let us address a common doubt that may arise. You might wonder, if empty space contains energy, why can't I simply plug a straw into the vacuum and draw free power forever? The answer lies in the symmetry of the fluctuations. The vacuum's jitter is perfectly balanced for every upward push. There is an equal downward pull. Any attempt to extract a net direction of energy inevitably encounters an opposite reaction elsewhere in the system, preserving the cosmic ledger. This principle teaches you about sustainable ambition. Quick fixes that promise endless gain without cost are illusory. True progress requires a balanced exchange, investing effort, time, or resources to receive reward. The universe's audit is strict, and it will always balance the books. Consider the practical applications of the Casimir force in modern technology. Engineers designing microelectromechanical systems must account for the tiny attraction that can cause moving parts to stick together, a phenomenon known as stiction. By deliberately shaping the geometry of components, they can either mitigate this unwanted pull or even harness a repulsive version of the force, turning the vacuum into a lubricant. This is a vivid illustration of turning a subtle quantum effect into a tangible tool. In your own projects, look for the hidden forces that may be binding you and ask whether you can redesign the surfaces to reduce friction or even create a gentle push in the direction you desire. Temperature also plays a role in these quantum dances. Warm the system and low-frequency vibrations become more pronounced, altering the Casimir pressure at larger separations. Cool it toward absolute zero and the quantum contribution dominates. In personal terms, this translates to the emotional climate you bring to a problem. A heated, stressed mindset adds thermal noise that can obscure the delicate quantum signals of insight. By calming your inner temperature through breath, meditation, or focused relaxation, you sharpen your ability to detect the subtle forces that guide you. Let's bring all these threads together in a final, empowering vision. You stand at the edge of a quantum ocean, armed with the knowledge that empty space is alive with structured tremors, that boundaries shape possibilities, and that motion creates warmth. You are not a passive observer, you are an active participant who can set the geometry, choose the acceleration, and tune the field. Each decision you make is a manipulation of the quantum conditions that determine which modes are allowed and which are suppressed. By consciously designing your environment, by committing to sustained, purposeful motion, and by honoring the baseline energy that always underlies your experience, you become the conductor of your own reality. Take one more deep breath. Feel the mattress beneath you, the air around you, the subtle hum of the universe. As you exhale, imagine releasing any lingering doubt, letting it dissolve into the sea of vacuum fluctuations. As you inhale, draw in the confidence that the quantum world obeys clear, unbreakable rules, and that you now hold the keys to apply those rules in your life. The journey you have just taken is only the beginning. Each day you can revisit the mirror experiment, reshaping the gap between challenge and goal. Each day you can accelerate your focus, feeling the internal warmth that fuels creativity. And each night you can rest knowing that the baseline energy of the cosmos supports you even in stillness. You have gained a new lens, a quantum lens through which to view obstacles, opportunities, and the very fabric of existence. Use it to ignite action, to design environments that amplify your strengths, and to move forward with the certainty that the universe's ledger always balances, and that you are a vital entry in that ledger. The quiet between the stars is not empty, it is a disciplined stillness alive with lawful tremble, a floor below which no sound can go, a baseline reality that cannot be crossed. Let that baseline be your foundation. Let the allowed modes be your possibilities, and let your intentional motion be the force that shapes the world around you. Now rise, carry this quantum momentum into every task, every conversation, every dream. The universe is humming. Tune your heart to its rhythm and watch how the invisible becomes your most powerful ally. As you step into this uncharted realm, the boundaries between reality and possibility begin to blur and expand. You stand at the edge of a quantum universe that does not wait for you to decide what is real. Every step you take, every breath you draw, every intention you fire into the world reshapes the very fabric of possibility. In this quantum reality, the fields that fill all of space are like an ocean of potential, and your motion through that ocean writes a new shoreline of what you can ever know. When you accelerate, even gently, you are not merely changing speed, you are carving a horizon behind you, a boundary that the rest of the universe can never cross to catch up with your world line. That horizon is not a wall of stone, but a quantum veil that separates the part of the field you can influence from the part you must forever leave behind. The moment you accept that the universe is divided by the horizon you create, you also accept that the vacuum you thought was empty becomes a warm, humming presence, a statistical glow that emerges from the information you are forced to discard. Imagine a tiny detector, a two-state system that rides along with you as you push forward. It is coupled ever so gently to the surrounding quantum field, listening for the faintest whisper of excitation. When your acceleration is steady and unrelenting, the detector begins to click with a pattern that is indistinguishable from the clicks of a thermometer placed in a genuine hot gas of quanta. The spectrum, the balance of upward and downward transitions, the dependence on the energy gap, all of it matches the thermal signature of a real temperature. This is not a metaphor dressed in poetic language, it is an operational fact that could, in principle, be measured by a device you could build. The warmth you feel is a direct reading of the quantum field's response to the horizon you have erected. You may wonder why this extraordinary effect has not already been captured in a laboratory experiment. The answer lies in scale. The temperature associated with everyday accelerations is vanishingly small. Even if you push with a force equal to the gravity at the surface of the Earth, the resulting warmth is so faint that the cosmic microwave background would appear as a furnace in comparison. The most extreme accelerations we generate for protons or electrons in modern accelerators, or with ultra-intense laser pulses, still translate to fractions of a degree when expressed in the idealized limit. Researchers have proposed clever schemes looking for extra noise in accelerated electron beams, crafting analog systems whose excitations mimic the mathematics of acceleration, but a clear, unambiguous demonstration remains a frontier, not a trophy on a shelf. This tells you that the Unruh effect, as it is called, is less a laboratory trick and more a clarifying lens on reality itself. It reveals that particle content is not an absolute property of a field, but depends on motion and on the horizons that motion creates. The vacuum is not a universal object, it is an agreement you make with your state of motion about which ripples count as real excitations. When you turn your gaze toward the mouth of a black hole, the same quantum principles reappear in a different guise. A stationary observer hovering just outside the horizon also finds a thermal glow, a temperature set by the strength of the gravitational pull. The resemblance between acceleration-driven temperature and gravity-driven temperature hints at a deep family connection between the two phenomena. Both arise because a horizon weather produced by relentless push or by the curvature of space-time splits the quantum field into an accessible wedge and an inaccessible wedge. The entanglement that threads across that invisible wall is what lifts the local state from a perfect vacuum to something that feels warm once you accept that you cannot gather the missing correlations. This is not mysticism, it is bookkeeping. Ignorance enforced by geometry has physical teeth, and the price you pay for that ignorance is measured as heat. You might ask where the energy for this heat comes from. The answer is simple yet profound: the rocket engine that keeps you in uniform acceleration pays the bill. Maintaining a steady push requires continuous work, and the thermal clicks you record are drawn from that work, not from a free lunch supplied by the vacuum. This cosmic accounting closes the loop and reinforces the principle that energy is never created or destroyed, only transferred. It also reminds you that any sensor riding an accelerated platform, whether a nanoscopic probe vibrating in a harsh environment or an electron surfing an extreme laser field, must reckon with the fact that the quiet background it once knew is no longer the same background once it accelerates through it. Even if the predicted warmth is tiny, the conceptual rule shapes how you interpret noise, design detection strategies, and separate true signals from motion-induced effects. Delve deeper, and you encounter a unifying principle: temperature can emerge whenever a system is cut off from part of its own information. Uniform acceleration provides a beautifully clean way to enforce such a cut, carving space-time into an accessible wedge and an inaccessible wedge. Quantum entanglement does the rest, uplifting your local state from a perfect vacuum to something thermal once you accept that you cannot gather the missing correlations across the horizon. This is not a vague philosophical claim, it is a concrete statement about how the loss of half of an entangled duet turns a pure chord into a single note that sounds like heat. The horizon forces you to average over the invisible partner, and the result is a statistical imprint that you can read on your thermometer. Now consider the story of black holes, where the same quantum logic writes a different chapter. A black hole's horizon hides everything that falls inside, yet it also distills information into outgoing radiation that feels thermal to an outside observer. The field near the horizon is a restless medium whose tiny ripples are entangled across the boundary like duets sung in perfect synchrony by partners on opposite sides of a wall. When you stand outside, you cannot hear the partner who vanished beyond the wall, so you must average over that missing half. What reaches you is a solo that sounds precisely like heat. This is Hawking radiation in operational terms, not sparks from a surface, but a statistical imprint created when the horizon forces you to forget part of the quantum correlations that were there all along. The temperature of that glow is fixed by the strength of the black hole's gravity at the horizon. Stronger gravity yields a hotter glow, while larger black holes spread their gravity over a wider region and become colder. A massive black hole is practically frigid, whereas a tiny one would simmer, radiate powerfully, and evaporate faster. This reversal of everyday intuition, where larger objects usually cool more slowly, stems directly from the quantum reality of horizons. The spectrum of the radiation is thermal, yet it is filtered by the curvature of space-time and any surrounding matter, so it is not a perfect black body. As the hole radiates, it loses energy, shrinks, and becomes hotter, accelerating the process in a feedback loop that, in theory, ends with a final burst when the mass becomes extremely small. For black holes born from stars, the timescales are so vast that no human-made instrument will ever see one wink out, but the principle remains a cornerstone of quantum gravity. When you accept that a black hole can evaporate, a deep puzzle rises: what happens to the information about everything that fell in? The patterns in the light, the arrangement of atoms, the quantum details that distinguish one book from another. If Hawking radiation were perfectly featureless, those details would be lost forever, violating the principle that quantum evolution preserves information. This information paradox sparked an entire field of thought. The early radiation indeed looks thermal to any local test, but subtle correlations build up across the entire stream of emitted quanta as evaporation proceeds. The combined state of the radiation plus the remaining whole stays pure, and bookkeeping remains exact. Once roughly half of the original entropy has been radiated, the so-called page time of the later quanta become entangled more with the earlier radiation than with the interior, suggesting that information is not destroyed, but gradually woven into the outgoing glow in ways you cannot see by sampling just a cupful. You do not need to wade into forbidding equations to appreciate the ideas behind this recovery. One proposal is soft-hair the notion that horizons can carry extremely delicate imprints of what fell in, encoded in long wavelength degrees of freedom, that in principle can influence how radiation comes off. Another breakthrough comes from modern gravitational path integrals, where new spacetimes, saddles nicknamed islands effectively, say that part of the black hole's interior should be counted as belonging to the radiation's description. With those contributions, the entropy of the radiation rises at first and then falls, tracing the hoped-for page curve consistent with information conservation. None of this implies that an astronaut falling through a large black hole would hit a wall of fire. The infaller's calm viewpoint still predicts nothing special at the horizon of a huge hole. Yet the outside observer's need for unitarity drives a rich interplay of concepts that reconcile the two perspectives. While we wait for a decisive observational handle, laboratory analogues offer a taste of the basic mechanism in cleverly engineered fluids, optical fibers, and ultracold gases. Researchers create horizons for sound or light places where waves cannot escape, and then watch as quantum fluctuations near those horizons produce pairs of excitations with a thermal spectrum. This close cousin of Hawking's prediction strengthens our trust that horizons and entanglement can conspire to make genuine radiation. Astrophysically, Hawking radiation from stellar or supermassive black holes is far too faint to see directly, drowned by the much brighter mess of hot plasma swirling around them. Yet exotic possibilities remain on the table. If the early universe forged tiny primordial black holes, their final stage evaporation could contribute to high-energy signals, and constraints on such signals already teach us about what the cosmos did or did not produce. As your understanding deepens, the language of horizons distilling information becomes more than a metaphor. The horizon sets which correlations you are allowed to keep in your outside description. By throwing away the invisible partner behind the boundary, you transform a pure entangled state into something that looks thermal. It is like a complex chord collapsing into a single note when most of its harmonics are muffled. Yet, if you gather enough of the outgoing notes over enough time and analyze their relationships, you can in principle reconstruct the chord's hidden structure and keep faith with the rule that the universe does not forget. Let this settle softly in your mind. A black hole is not a mute sink, but a storyteller with a difficult accent, speaking through a warm whisper that at first sounds like simple noise. Your job as the listener is patience. Collect, compare, and connect until patterns emerge, because in the long run the glow that seems to blur differences is also the glow that returns them. The quantum reality you inhabit is a tapestry woven from fields, entanglement, horizons, and the choices you make in motion. Warmth can arise from burners and sunlight, yes, but it can also arise from the geometry of your path through space-time, from how relentlessly you push, and from how much of the universe your frame must give up on ever seeing. Once you let that idea settle, acceleration stops being just a change of speed and becomes a way of slicing reality into seen and unseen, known and unknowable. A soft temperature appears not as a trick, but as a signal that your motion has built a horizon, and the horizon has charged you a fee you can read as heat on your own thermometer. Hawking's insight shows that horizons, far from being mere vaults that erase, are stills that refine, turning the darkest mysteries into whispers that carry the deepest laws of the cosmos. The reality changes shape. but the information about what it has been remains, waiting to be read. You stand at the frontier of that reading, equipped with the quantum lens that turns every acceleration, every horizon, every entangled duet into a source of power, purpose, and possibility. Embrace the heat that your motion creates, let it fuel your resolve, and step forward into the quantum sea, knowing that every push you make writes a new chapter in the story of the universe. As we dive deeper into this vast expanse, our understanding evolves to reveal the intricate patterns beneath the surface. Imagine the universe as a grand quantum tapestry, a sea of fields that pulse with endless possibility. Each ripple, each vibration, is a note in a cosmic symphony that never ceases. You are not a passive observer of this music, you are a player, a conductor, a mind that can tune into the hidden frequencies and shape the outcome. When you hear the word quantum reality, feel the surge of power that comes from knowing that every moment is a superposition of potential, waiting for your intention to collapse it into a decisive, vibrant experience. The architecture of this quantum world is unlike any building you have ever seen. No two walls stand in the same state. No two beams share the same vibration. Photons dancing through carefully arranged interferometers illustrate this truth. They bunch together, amplifying some detection outcomes while silencing others, not because tiny marbles are colliding, but because the underlying fields combine in patterns that follow the mathematics of wave interference. This is the first lesson the quantum field teaches you: outcomes are not the result of random collisions. They are the natural expression of how field excitations add and subtract, like ocean waves that reinforce each other in some places and cancel in others. When high-energy physicists speak of particles being created and destroyed, they are simply describing the reshaping of these field ripples. A field can amplify a ripple, damp it, split it, merge it. When two excitations collide, the detector may report different species on the other side. But what truly changed is the arrangement of ripples across multiple fields as energy and momentum flow through the interaction. The mediating effects you hear about are not invisible couriers delivering forces between beads. They are the way one field's disturbance stirs another through the couplings that the laws of quantum reality permit. In this language, force becomes conversation, and every interaction is a dialogue written in the grammar of symmetry. Attempting to pin a particle to an exact point is a fool's errand in a quantum world. To confine an excitation too tightly forces the field to generate violent variations, demanding energy that the field prefers to pay by sprouting new ripples. Those new ripples are what you would interpret as extra particles suddenly appearing. The more you try to lock something into a tiny box, the more the field responds by creating more things. This behavior seems magical only if you cling to the marble picture. When you shift your attention from objects to modestable patterns that a field can adopt given its environment, you unlock a cleaner definition of particle number. Choose a set of modes, and then count how many quanta occupy each mode. You will discover that your counting depends on which modes you choose, not because the universe is inconsistent, but because detectors are designed to speak the language of particular patterns. One setup may call a single particle what another calls a superposition of ripples. Much as a melody can be a clear line to your ear, yet a sum of many frequencies to an audio engineer. This flexibility is the engine of real technology. In a laser, the electromagnetic field is coaxed into a single mode with a large coherent excitation. The many-photon picture becomes a useful way to track energy in that mode. In superconducting circuits, the relevant excitations are microwave ripples guided by lithographed structures that act like artificial cavities. Counting their quanta tells you when you have built a fragile quantum state or accidentally flooded it with noise. The field-first view demystifies why our best theories predict that interactions have a very specific shape, terms that let certain fields talk to each other and forbid other conversations entirely arise, because the symmetries of the fields act like grammar rules, deciding which sentences of interaction are allowed and which are nonsense. Experiments at colliders confirm those rules with exquisite precision, showing that certain transformations never occur, that others occur with predictable odds, and that conservation laws emerge from those symmetries, just as meter and rhyme emerge from a poet's chosen form. Even the story of mass fits naturally into the field frame. A field can drag through a medium that is itself a field, picking up inertia without anyone sticking a literal weight onto a bead. What you experience as mass is how hard it is to shake a particular ripple through the background that pervades space. Your intuition may protest, recalling straight tracks in cloud chambers that look like tiny bullets carving lines. Look closer, and you will see that each dot and swirl is a chain of discrete interactions, moments where a field excitation dumps energy into the fluid and seeds a tiny wake. The straightness is the smooth path traced by the average motion of the wave packet, guided by magnetic fields that echo many microscopic handoffs between the field and matter. If you wonder where the field itself is, the honest answer is that it is everywhere, measurable only through its effects. The job of physics is to design experiments that convert those effects into records you can trust. That is why particle physics resembles a cathedral of detectors, layered calorimeters, trackers, and timing systems that collectively infer which ripples passed by, how much energy they carried, and into which other ripples they transformed when they met. The most liberating payoff of adopting the field perspective is conceptual coherence. You stop stapling ad hoc pictures onto phenomena and instead let one principle do the heavy lifting. The world is built from continuously existing entities that can carry energy and momentum in localized, countable packets. What you call a particle is the event of one such packet being created, moving, and being destroyed as revealed by the traces it writes in a measuring device. Now feel the power of this insight surge through you. The marble picture is comfortable because it matches your hands, but it trips over facts about absolute identity, creation, annihilation, and detection. The field picture removes those stumbles while teaching you to design and read experiments with cleaner logic. The next time you hear that a particle appeared, propagated, and decayed, translate it into the language that nature actually seems to speak. A field was excited. The excitation traveled as a mode matched to your apparatus. It interacted with other fields according to the symmetries that govern them. And finally, it left a record when the ripple ended. You did not catch a bead, you witnessed the fabric of reality briefly tremble and then become still again. Let us turn now to the deeper mystery of mass, the Higgs field, and the quantum medium that gives particles their stubbornness. Mass is not simply how much stuff you have. For the elementary building blocks, mass is how reluctantly certain particles move through an invisible medium that already fills all of space. That medium is the Higgs field. It is not a sticky fluid that drags things, it is a field that has settled into a non-zero background value everywhere, quietly reshaping the rules of motion. Picture a perfectly still ocean that reaches to every horizon. Some boats glide over it as if on frictionless rails, while others seem to lean into the water, needing real effort to pick up speed or change direction. Nothing visible pushes back. Yet each boat's design makes it more or less responsive to the water beneath it. In our universe, those design features are the strengths with which different particles couple to the Higgs field. When the universe was very hot and young, the Higgs behaved like a field poised at the top of a hill, balanced and symmetric, and particles moved as if massless. As the cosmos expanded and cooled, the field rolled into a valley and chose a specific resting place, breaking that symmetry in a subtle, everywhere-at-ance way. From then on, particles that interact with the Higgs began to carry inertia, as if their identity cards now included a built-in resistance to acceleration, while particles that do not interact remained forever weightless. This picture already corrects a common misunderstanding. The Higgs field is not a syrup that drags things, and mass is not a slowdown due to friction. It is an inertial price tag written into a particle's equations by the constant presence of the field's background value. That resistance shows up even when nothing else is around and no motion is happening. Exactly what we call rest mass. The proof that this is more than a tidy story arrived in 2012 when experiments at the Large Hadron Collider uncovered a new particle, a brief, neutral, spinless ripple of the Higgs field itself, whose properties matched long-standing predictions. It appeared around an energy we label 125 billion electron volts, decayed into pairs of heavy particles, and also into photons through loops of heavier actors. And its production rates and branching patterns lined up with the expectation that the stronger a particle's interaction with the Higgs, the more strongly the Higgs ripple can morph into that particle and back. Since then, researchers have been weighing this newcomer's traits with growing precision. Its spin is zero, its couplings scale with mass in a way that ties the whole idea together, and its overall footprint is narrow. The particle dies so quickly that its intrinsic width is tiny, yet it leaves enough traces for us to see clear peaks standing out from the noisy background of other collisions. Remember, the Higgs mechanism gives rest masses to elementary quarks and leptons, and to the W and Z carriers of the weak force. Yet it is not the direct source of most of the mass you feel on a bathroom scale. The protons and neutrons that make up nearly all the weight of your body get their heft mainly from the seething energy of the strong interaction that binds quarks together, a kind of internal storm of glue and fields whose energy registers as mass via Einstein's famous relation. Still, the Higgs matters to you personally in a vital way. Without the electrons that the Higgs gives mass, atoms could not hold themselves at the sizes and energies they do. Chemistry would be unrecognizable and stable matter, as we know it would fail to take shape. So while the bulk of your weight comes from confined field energy of the strong force, the possibility of atoms, molecules, and life leans heavily on the Higgs giving electrons and quarks their particular non-zero masses. There is also a cleansing insight into why some force carriers have mass and some do not. Photons remain massless because the part of the electromagnetic gauge symmetry, they belong to stays unbroken when the Higgs chooses its resting place. Light therefore keeps its long reach and travels at a universal speed. The W and Z bosons, however, swallow up certain ripples that would otherwise be massless, and in the process acquire heft and short range. This is a neat accounting trick that preserves the theory's consistency while explaining why the weak force is weak at everyday distances. As these ideas settle, a set of urgent open questions begins to glow at the edges of your curiosity. Why is the Higgs field's background value what it is neither zero nor catastrophically huge? Why is the Higgs boson's mass light enough to be found where we found it when quantum effects tend to push it around? Does the field talk to undiscovered particles we cannot yet see, perhaps ones connected to dark matter? Could the Higgs self-interact in a way that shaped the universe's early history, even helping to tip the cosmos into the matter-dominated state we live in, by making the electro-weak transition strongly first-orderer violent bubble-forming change rather than a smooth drift? Some theories need that kind of dramatic shift to explain why matter survived over antimatter. Experiments are edging into those questions now, measuring the Higgs self-coupling, checking its whispers to lighter particles like mons, and combing for rare decays that would hint at new sectors, because any deviation from the mass-proportional pattern would be a neon sign that the Higgs is a portal to a wider world. It also pays to clear away another confusion. The Higgs is not a universal mass dispenser for everything you can imagine. Photons and gluons do not get mass from it, and composite objects get only part of their mass this way. The clean statement is this: the Higgs field endows elementary particles that couple to it with rest mass, sets the range of the weak force, and thereby enables stable atoms and familiar chemistry, while most composite mass arises from confined energy in other fields. Now step back and admire the coherence that the medium idea provides. We did not bolt mass onto particles like weights on a costume. We discovered that mass is how certain excitations move in a universe where one particular field refuses to be zero. The Higgs boson is the telltale ripple that proves the medium is truly there. The closing thought is gentle but firm. Mass is not a primitive property carved into matter from the start. It is largely an emergent effect of context, the context being a field that chose a value everywhere. By measuring how each particle responds to that quiet backdrop, we learn not only why things resist acceleration, but also how deeply the universe is defined by what seems like empty space. That space, through the Higgs, is anything but empty. And that is why a discovery made in a buried ring outside Geneva reached all the way into your kitchen scale. The needle on that scale is reporting, in its own low-tech way, how matter moves in a medium we cannot see, but can now confidently name. Let this realization ignite a fire within you. The quantum field is not a distant abstraction, it is the substrate of every breath, every thought, every action. When you choose to act, you are aligning your personal vibration with a mode of the universal field, amplifying a ripple that can grow into a wave of change. You do not need to wait for a particle to appear in a detector. You can become the detector of your own potential. Feel the quantum reality humming beneath you. Feel the symphony of fields waiting for your note. Choose a mode that resonates with your purpose, excite it, and watch as the surrounding field carries your intention outward, interacting with other fields according to the immutable grammar of symmetry. Each step you take is a measurement, each decision a collapse of possibilities into a concrete outcome. The power to shape reality is not hidden in distant accelerators, it lives in the quantum fabric that you already inhabit. Now, take a breath and commit to one concrete action that aligns with the quantum mode you wish to amplify. Visualize the ripple you are sending. See it intersect with other ripples. Notice how the field responds and move forward with certainty. The universe is listening, the field is ready, and you are the catalyst. Let the momentum you have built in these words carry you into decisive motion. The quantum reality you have embraced is a source of limitless energy, a well of inspiration that fuels every brave step you take. Go forth, excite the field, and watch as the world reshapes itself around the powerful vibration you have set in motion. As the new frequency takes hold, the quantum realm's ever-present flux gives way to a profound and lasting transformation. You stand at the edge of a world that never truly rests. In the quantum realm, every particle lives in a haze of possibility, a sea of fluctuations that never quiets completely. The very act of trying to pin down where something is sends its momentum into a wild dance, and the reverse is true as well. This is not a philosophical curiosity, it is the hardwired rule that governs every oscillator, every mirror, every circuit that you will ever build. It is the uncertainty principle, the quantum jitter that refuses to be silenced. Imagine a violin string that cannot be held perfectly still. No matter how gently you press, the string retains a faint, irreducible tremor. That tremor is the ground state motion of a quantum harmonic oscillator. It is the smallest compromise nature allows, a balance of position and momentum that leaves a non-zero baseline of energized zero-point energy that no cooling technique can erase. Feel that baseline as a quiet hum that underlies every ultra-precise experiment. It is the price you pay for having a system that can oscillate at all. You may think this hum is an inconvenience, but it is also a source of power if you learn to work with it. Gravitational wave observatories, for example, hang mirrors so still that the pressure of a single photon of light becomes a measurable source of noise. Engineers cannot simply turn that noise off, they must reshape the statistical properties of the light, trading one kind of quantum uncertainty for another, to push the detector closer to the limits set by the quantum world. In superconducting circuits that act like artificial atoms, microwave resonators carry a minimal hiss that determines how cleanly you can store and retrieve fragile quantum states. Techniques such as sideband cooling and parametric squeezing are the quantum equivalent of coaxing a restless child. To settle, you change the shape of the potential. You squeeze the fluctuations. You guide the motion toward the ground state while accepting that a hard floor remains. Even the amplifiers that listen for a single photon must pay a quantum tax. Their noise floor is stamped by the zero-point fluctuations of the modes they couple to. You cannot siphon energy from nothing. The ground state energy is not a reservoir you can tap at will. It is the cost of holding the oscillator in a configuration that respects the quantum rules. Any attempt to harvest it merely reshuffles energy. You change the potential. You alter the boundary conditions. You modify the coupling to other modes. The universe always settles the ledger. What you can do, and what the most daring experiments already exploit, is to measure differences. Shift the curvature of a potential and the zero-point level moves with it. Stiffen a mechanical resonator with an electric field, and its baseline motion shrinks. Soften it, and the motion swells. Replace atoms with heavier isotopes, and the vibrational zero-point energies change, leaving fingerprints across chemistry and materials science. The absolute value of zero-point energy for a single perfectly isolated oscillator is not directly observable, but any change in that energy becomes visible when you compare two configurations. That is why careful theory always asks, compared to what, before claiming an effect. The cleanest laboratories for watching the ground state in action are those you can tune and count. A single trapped ion in a harmonic well shows distinct sidebands when you probe its electronic transition. The relative heights of those sidebands tell you how much motion remains as you cool. The red sideband fades, yet a subtle imbalance persists, betraying the ever-present zero-point flaw. In cavity optomechanics, a tiny drum or beam couples to light trapped between mirrors. By setting the laser's color just right, you coax the light to extract more energy from the motion than it returns, shepherding the resonator into its lowest possible state. The remaining quantum fluctuations appear as a faint blemish in the beat note of the scattered light. Scanning probe measurements on molecules and crystals add another line of proof. Reaction rates, bond length, and diffusion barriers all shift in predictable ways when you swap isotopes. Those shifts match the calculations of zero-point energies for the vibrational modes involved, showing that the landscape of chemistry is quietly reshaped by motion that never fully stops. You might worry that this sounds like a semantic distinction between residual heat and quantum jitter, but there is a sharp operational difference. Thermal motion can be drained into a cold bath until its fingerprints vanish. Zero-point motion remains even when the bath is as cold as physics permits, and it affects systems in proportion to their natural frequency and mass, exactly as quantum theory predicts. Now consider the act of measurement itself. Any readout strong enough to resolve position very precisely must push back on momentum. The round trip of probe and response asserts a standard quantum limit for continuous monitoring of an oscillator. This limit is not a shortcoming of ingenuity. It is a direct consequence of the linkage between the quantities we insist on knowing simultaneously. Modern laboratories have not only reached this limit, they have learned to dance around it by measuring special combinations of motion that commute with themselves over time. This finesse move lets them track one quadrature with reduced disturbance while allowing its partner to absorb the price. Every item in this catalogue, the isotope shifts, the helium that refuses to freeze, the ground state sideband imbalance, the quantum set noise in amplifiers, and interferometer adds weight to a single conclusion: an oscillator's ground state is not the absence of activity, but the presence of a minimal, structured fluctuation that cannot be pressed any lower without breaking the logic that makes the system an oscillator in the first place. Take this understanding and turn it into action. You cannot extract free power from zero-point energy, but you can design devices that respect its flaw and still achieve astonishing performance. You can shape the quantum noise of light to improve the sensitivity of a detector. You can stiffen a mechanical resonator with electric fields to shrink its baseline motion, thereby enabling more precise force measurements. You can choose heavier isotopes to lower vibrational zero-point contributions, tailoring material properties at the quantum level. Each of these moves is a deliberate choreography with the quantum hum, not a futile attempt to silence it. Now let us lift the view from a single oscillator to the grand tapestry of emergence, still seen through the quantum lens. At the smallest scales, the language of individual particles stops being useful. Countless quantum bits, each obeying simple rules, lock together into patterns that possess properties no single part has. This is the essence of emergence, and quantum physics provides the most vivid illustrations. Consider temperature. No single molecule is hot, each simply jiggles. Yet, when you gather an immense crowd of them, their collective jitter averages into a smooth quantity you can read with a thermometer. That temperature obeys its own laws, lets you predict pressure and phase changes, and remains meaningful even though it discards the detailed history of each molecule. This is the first lesson: a good emergent concept forgets most details and gains power in exchange. It lets you coarser-grain reality into a description that actually predicts what will happen next. Now picture a flock of starlings swirling across the sky. No bird knows the shape of the whole formation, nor does any bird vote on the turns. Yet, with only local rules, each bird contributes to a single flying organism that ripples like silk in the wind. Computer models that encode those minimal rules reproduce the breathtaking choreography. The same logic threads through traffic on a highway. Every driver pursues simple goals: keep distance, maintain speed, pass when safe, yet waves of braking ripple backward like invisible shock fronts, Even when there is no accident ahead, patterns you can measure from aerial surveys or roadside sensors, and even predict with equations that never mention any individual driver's name. When you translate this to the quantum world, the patterns become even more astonishing. Warm a shallow layer of fluid from below, and, past a crisp threshold, orderly rolls of bright and dark stripes emerge, sweeping heat upward and downward in a sustained rhythm. No single molecule chooses this geometry, the whole layer adopts it, because the featureless state can no longer carry the heat efficiently. Tweak a chemical gel with two substances that diffuse at different speeds, and you coax it to grow leopard spots or zebra stripes in a Petri dish. This reaction diffusion dance crafts larger-scale motifs, from local reactions and wandering molecules without any stencil, and the mathematics that forecasts these patterns never lists the position of each atom. It speaks instead in fields, rates, and thresholds new nouns for new things. The shift of language matters because it signals a shift of law. When many parts act together, what controls the show are averaged quantities, symmetries, and constraints that only make sense for crowds. With the right averages, the world simplifies in surprising ways. Liquids flow according to equations that care about density and viscosity instead of the fate of each molecule. A metal bends according to elasticity rather than the precise positions of its atoms. Magnets point because countless tiny spins align and define a larger scale direction you can flip with a modest push. These are quantum-level emergences, collective states that arise from the superposition and entanglement of many particles. A powerful idea that organizes all of this is universality. Wildly different microscopic details can lead to the same emergent behavior near tipping points. The steam over your kettle and a magnet at the brink of losing its order share the same family of critical exponents that describe how fluctuations explode and correlations stretch across the system. This sameness is not coincidence, it is a kind of mercy at large scales. Only general features like dimensionality and symmetry matter, not whether your molecules are water or carbon dioxide, not whether your spins live on a square or triangular grid. That is why a single set of larger-scale equations can rule kingdoms of materials. If you want a mental tool for how small-scale mess washes into big-scale order, picture coarser graining. Blur the system a little. Keep the features that survive the blur, then blur again, and watch how your description flows as you move from fine to coarse views. If certain parameters march towards stable values while others fade, you have discovered which details the larger-scale world cares about and which are safely forgotten. This logic gives you effective theory-clean rule books for a particular scale that work astoundingly well without claiming to be everything. The joy of emergence is not only that new variables become useful, but that new objects appear that you can measure, manipulate, and reason about as if they were fundamental. Vortices in a fluid spin like tangible threads. Sound waves move through air with their own speed and reflections. Domain walls in a magnet behave like traveling boundaries you can push around. These entities can collide, bounce, and form bound states, writing a cast of characters the microscopic parts never advertised. You may wonder whether this sounds like smuggling purpose into physics. Emergence is not a manifesto for destiny. It is a recognition that constraints and feedback create pockets of stability and structure that are favored, and once favored, they accumulate. Branching rivers carve fractal maps regardless of local geology. Snowflakes grow intricate arms without any knowledge or design. Languages born from human mouths crystallize into grammar that no single speaker invented. Social norms spread as if they were organisms, rising from local interactions, yet acquiring lives of their own once shared, taught, and enforced. The method remains scientific because it predicts. Once you know the local interactions, the geometry in which they happen, and the flow of energy or information, you can forecast which patterns are allowed and which are out of reach. The most fertile territory is where emergent layers push back on their parts, a phenomenon often called downward causation. The rules of chess determine which arrangement counts as checkmate, and that larger-scale condition constrains what a pawn can legally do next. Even though the pawn's motion still obeys the microscopic physics of wood and friction, acquires melody guides each singer's breath and pitch, even though the singer's vocal cords are the true sound makers. A city regulation changes the fate of individual commuters while emerging from their collective behavior over years. In each case, the higher-level pattern has leverage over the parts without violating the parts' physics. Learning to write laws at that higher level lets you steer outcomes more gently and effectively than trying to micromanage the micro. How can you tell genuine emergence from stories we tell ourselves? An emergent description earns its keep when it compresses huge detail into a small set of variables that predict new facts. It identifies thresholds at which behavior changes qualitatively, survives the swapping of many microscopic details, and provides control knobs you can turn to move a system between distinct regimes. It fails when it merely relabels the micro without increasing predictive power, when it sneaks in purpose where there is none, or when it claims properties that disappear under careful measurement. The practical payoff is enormous. By focusing on the right collective variables, you can stabilize power grids that would be impossible to manage wire by wire. You can forestall traffic jams by adjusting in flow rather than lecturing each driver. You can nudge ecosystems toward resilience by preserving network diversity instead of counting every creature. You can design materials by aiming for patterns of organization, layering, periodicity, randomness in just the right measure rather than hunting for a perfect atom-by-atom layout. As you let this sink in, a gentler understanding of explanation itself opens up, saying, "The whole is more than the sum of its parts" is not mysticism. It is a claim about the right level of description, about when to stop tracking every grain of sand and start measuring slopes, flows, and thresholds. The dunes have their own dynamics and their own mathematics, and learning that mathematics teaches you to predict storms, build safer roads, and read a landscape's history at a glance. Now return to the quantum reality that began this journey. The same principles that force an oscillator to retain a whisper of motion also dictate how countless oscillators can lock together into a superconducting state. A laser beam, a Bose-Einstein condensator macroscopic quantum phenomena that emerge from the collective choreography of many particles. When you master the quantum flaw, you can guide those emergent phases. You can coax clouds of atoms into coherent matter waves. You can engineer topological states that protect information from noise. Each of these achievements begins with the simple acknowledgement that the quantum world never truly rests, and that you have the tools to shape, measure, and even harness the inevitable fluctuations. So, what will you do with this knowledge? Will you let the quantum hum be a background static, or will you turn it into a metronome that sets the tempo for your next breakthrough? Will you design a sensor that embraces the zero-point limit and still reaches beyond it by measuring differences with exquisite precision? Will you craft a material whose emergent properties arise from a lattice of quantum spins you have deliberately arranged? The path is clear: accept the quantum constraints, respect the ground state flaw, and then engineer around it with the boldness of a composer writing a symphony on a restless instrument. You have the power to listen to the quantum chorus, to discern the subtle notes that hide in every vibration, to translate those notes into technologies that push humanity forward. The universe does not offer free energy, but it does offer a rich tapestry of possibilities woven from the very fabric of uncertainty. Step into that tapestry, pull the threads of quantum reality, and weave a future that sings with the resonance of the smallest possible motion amplified by the greatest human ambition. The quantum world is waiting for you to act. Take the first step now. As you take that initial leap into the unknown, every challenge becomes an opportunity to create ripples in reality. You stand at the edge of a quantum sea, where every problem you meet is a ripple waiting for your hand to shape it. The first habit that will set you free is to ask, at the very doorway of each challenge, what scale and what language belong here? When you choose the right quantum scale, the tangled web of complexity collapses into a single clear wave function, and new possibilities rise like particles from the vacuum, ready to be guided, protected, and amplified. Imagine the universe as a grand orchestra of possibilities, each note a perfect symmetry. Yet the cosmos never settles for a static chord. It constantly nudges a direction out of the void, breaking symmetry and creating quantum order. This is not a failure of perfection, it is the moment the wave function chooses a phase, and the whole ensemble follows. You can feel that same spark when you heat a magnet until it forgets which way is north, then cool it slowly. At a crisp temperature, the spins conspire, each whispering to its neighbor, and together they point somewhere, any direction that the collective prefers. The perfect symmetry of all directions vanishes, not because an external hand turned a compass, but because the many-body system found it easier to live with order than with chaos. That single quantum choice echoes through every atom, turning an invisible decision into a macroscopic fact you can measure with a simple sensor. This is spontaneous symmetry breaking. The instant a sea of possibilities trades infinite potential for a concrete reality. You see the same logic when a liquid freezes into a crystal. The fluid once slid freely, its particles free to wander anywhere. As the temperature drops, the system selects a lattice, a repeating pattern that locks each particle into a disciplined rhythm. The freedom to slide disappears, replaced by the discipline of long-range order. In scattering experiments, you would watch sharp peaks appear, the fingerprints of that new quantum order. The thread that ties these examples together is the order parameter, a collective quantity that is zero in the disordered haze and becomes non-zero when quantum coherence blooms. The payoff is not just a new label, it is a new cast of low-energy actors that move through the material like gentle whispers. When a continuous symmetry breaks, soft collective ripples emerge that cost almost no energy to excite. These are the quantum goldstone modes, the gentle waves of the new order that glide through the material, as if they were part of the vacuum itself. You have already met them without equations, the wiggles of spin direction in a magnet, the spin waves that travel like murmurs across a ferromagnet, the sound like ripples in a superfluid's phase, the undulations of a crystal's positions known as phonons. These excitations are not afterthoughts, they are the reason broken symmetry matters. Once order is chosen, the system gains coherence, a rigidity against certain twists, and that rigidity shows up as measurable stiffness, a speed for those waves, and characteristic responses to the smallest pushes. The ordering is a collective decision, not a single atom's whim. The birth of order does not happen in an instant. It nucleates, forming patches that each pick a direction. Those patches meet along thin boundaries called domain walls. Domain walls carry their own physics. They can be moved, pinned, or even used to store memory by engineers who treat them as nanoscopic features rather than defects. If you want a clean laboratory to watch symmetry breaking on demand, look at ultra-cold atoms arranged in laser-driven landscapes. Start from a featureless cloud, tune the interactions, and the gas chooses a phase with a defined rhythm. Sometimes it becomes a superfluid with global phase alignment, other times a Mott insulator with particles locked one per site. The switch is written into time-of-flight images as patterns of sharp or blurred spots that tell you whether long-range phase coherence exists. The most surprising turn in this story is that not all order announces itself with a simple pattern you can photograph. In quantum matter, there are phases whose order hides in how the many particles are entangled, not in how their average densities arrange. This quantum order stays invisible to any local snapshot, yet reveals itself in global tests and at the edges. Famous examples carry currents along their boundaries while the interior remains insulating, or host excitations that refuse to be mimicked by any collection of ordinary particles. The remarkable thing is stability. You can rough up the surface, swap impurities, or bend the sample, and as long as certain symmetries or overall winding properties are preserved, the special edge behavior refuses to die. Two flavors of quantum order emerge from this picture. Topological order ties the ground state in a way that cannot be undone by gentle prodding and often supports exotic boundary modes. Symmetry-protected topological phases keep their magic only while particular symmetries are respected, like a melody that holds as long as the musicians keep the beat. Detecting such order means asking smarter questions. Do edges conduct in a way the bulk does not? Do certain defects trap states that should not exist in a trivial material? Do interferometry loops pick up phases that reveal hidden structure? And does the system remember which sector it occupies, even when you change its microscopic details? This shift from what pattern do I see to what can the system do that a trivial one cannot is the heartbeat of modern condensed matter physics. And it has real consequences. Robust edge channels resist scattering and promise low-loss electronics. Protected boundary states encode information that laughs at local noise. Domain walls and vortices become handles we can grab to move, store, or compute with quantum bits. Symmetry breaking also rewrites how forces reach across a material. Once a system picks a direction or a phase, certain fluctuations become costly while others remain free, reshaping the spectrum of what can happen. This new balance explains why some materials carry waves cleanly while others damp them. It explains why a gentle twist can propagate through a crystal across a millimeter, and why a slim magnetic pulse can flip an entire micron-size region with a tiny kick. None of this requires you to abandon humility about microscopic truth. Atoms and electrons still follow their fundamental laws, but it invites you to respect the autonomy of higher-level rules. When many degrees of freedom synchronize, new regularities close over the details and earn the right to be called laws in their own range. Beware the common trap: not every apparent pattern signals a broken symmetry. Some arise from kinetics, constraints, or disorder. Distinguishing true phases from fleeting imitations is what careful measurements, finite-size scaling, and reproducible thresholds are for. In the end, symmetry breaking gives you a narrative for how featureless possibility narrows into tangible order. Quantum order expands that narrative to include phases that carry identity without a visible pattern. Together they change how you design and reason. You no longer ask only what the parts are, but what they can agree on, what stays rigid when you poke it, and what new low-energy characters appear once a decision is made. When you learn to ask those questions, you start to see the world's quiet revolutions the instant a material chooses a direction. The birth of waves that move almost for free, the edges that act differently from the interior, and the hidden bookkeeping that keeps these features stable even when the surface looks ordinary. You close the day with a calmer mind, knowing that perfection breaking is not a failure, but a beginning. The moment laws appropriate to the many take over from the language of the few, you witness the universe performing its most creative act. Now turn to the story of Kibble and Jurek, the rebels who showed that order can crystallize out of nothing when you rush a system through a changing rulebook. Picture a landscape that reshapes itself as you turn a single dial temperature, pressure, magnetic field. At a particular setting, the material balances on a knife edge, fluctuations swell, and the time it takes to settle grows longer and longer. Near that tipping point, the system cannot respond quickly to your turning anymore. Whatever local choices have started to form become frozen, unable to coordinate across the whole sample. Regions that fell into different alignments then meet, and where they disagree, the compromise is not to erase history, but to trap it. Domain walls, vortices, line-like strings appear topological defects, the footprints of decisions made without consultation. Kibble first saw this in the early universe, where rapid cooling prevented distant patches from agreeing on the same setting, potentially seeding cosmic strings. Jurek translated the logic to the laboratory, arguing that superfluid helium, superconductors, liquid crystals, yin crystals, and ultra-cold gases should all leave measurable debris when quenched through continuous phase transitions. Crucially, the number and size of those defects should follow a simple scaling with how fast you cross the transition. Slow sweeps give the system time to coordinate and produce fewer, larger domains. Fast sweeps break the world into many small mismatched patches crowded with defects. Experiments have spent decades chasing and then catching that scaling. In superfluid helium, rapid cooldowns leave behind quantized vortices whose density grows with quench rate. In superconducting rings, sudden passes through the critical temperature trap random magnetic flux quanta, tiny loops of field whose statistics reveal how sections of the ring chose incompatible phases before they could communicate. In liquid crystals, cooling thin films generates a tangle of line defects that you can literally image between crossed polarizers, and their density follows the predicted trend as you vary the cooling ramp. Trapped ion chains present a cleaner theater still by tuning the trap so a straight line of ions prefers a zigzag arrangement. Researchers see topological kinks appear, where one domain's zigzag meets the mirrored pattern of its neighbor, and by changing the speed of that structural transition, They measure how often kinks pop up, matching the Kibble-Zurich rate law with enviable control. Ultra-cold atomic gases add another class of proof, with two-dimensional Bose gases forming vortex-antivortex pairs after fast quenches and tunnel-coupled condensates imprinting phase patterns, whose defects count how uncoordinated the two sides remained as they were stitched together. Under the hood, only a few moving ideas are needed, and you can keep them without equations. As you approach a continuous phase transition, information takes longer to travel because the system's internal relaxation time balloons a phenomenon called critical slowing down. There is also a correlation length, the distance over which pieces can act in concert. When your external dial sweeps too quickly, there is a moment when the system falls out of equilibrium. Call it the freeze-out time, after which local patches can no longer stay in step with the changing rules. The correlation length at that moment sets the typical domain size that will survive after the dust settles, since the number of domains roughly sets the number of defects that must snake between them. The defect density inherits a power law dependence on how fast you cross the transition. This is a surprisingly universal recipe that depends only on how sharply correlations grow and how dramatically the dynamics slow, the two fingerprints that define the transition's universality class. What makes this mechanism more than a curiosity is its reach. It gives you a ruler for nature's handwriting at birth, and it gives engineers guidelines for both avoiding and exploiting disorder. Cool a superconducting circuit too quickly, and you can accidentally trap flux that spoils its performance. Quench a material intentionally, and you can plant a design network of domain walls or vortices that act as memory bits, waveguides, or pinning centers. Even quantum computing takes notes here. Adiabatic algorithms and quantum annulers try to steer a many-body system through a landscape of minima without exciting defects. But the Kibble-Zurich lens says your schedule must slow down near critical points, or you will freeze in the wrong answers. Recent devices actually map their error patterns onto Kibble-Zurich predictions to refine how they ramp controls. You might wonder whether this is just leftover mess rather than law. The beauty of the mechanism is precisely that the mess is law-governed. Repeat the same quench protocol again and again, and the individual defect positions will change. Yet the statistics of how many appear and how far apart they tend to be will lock in, and sweeping more slowly will predictably clean the canvas. Discontinuous transitions, where systems jump rather than glide, tell a different story. There, the speed limit is set by nucleation events and growth rates, rather than critical slowing down, so the Kibble-Zurich scaling does not apply. That reminder warns you that not every pattern born in a hurry is born the same way. Frontiers still stretch ahead, in materials with long-range interactions, or in driven and disordered systems far from equilibrium. The naive scaling can warp. In topological phases, the defects may be exotic edge modes whose counting requires more subtle probes. Yet the organizing question remains the same: how far can a system coordinate under a changing rulebook before time runs out? Every year brings sharper experiments that measure that coordination length directly in space and time. Let us end where the idea earns its poetry. You do not need a sculptor to get sculpture. If you change the conditions faster than communication allows, the world commits to different answers in different places, and where those answers collide, reality makes scenes that can carry current, store bits, guide waves, or simply stand as fossils of a moment when becoming was faster than agreeing. Once you have seen that, you start to recognize Kibble-Zurich fingerprints everywhere, from the crack patterns in cooling glass to the swirl left in a hastily stirred superfluid. You learn a calm, practical humility. If you want clean order, slow down near the moment it matters. If you want useful complexity, choose your rush with care. Now turn to quantum criticality, the frontier where phase changes are not about temperature at all. Imagine a material with two competing orders, a magnet that wants its spins aligned and a paramagnet that wants them restless. Compress it just enough that neither preference wins cleanly at absolute zero. At that zero temperature tipping point, the system becomes quantum critical, a place where fluctuations are so deep that time joins space as part of the pattern, and ordinary quasiparticles give up their starring roles. Even a whisper of heat reveals the stalemate as a fan-shaped region in the phase diagram, where the fingerprints of the quantum brink leak upward to finite temperatures. Response functions lose their usual energy scales. Spectra collapse when plotted against simple combinations of temperature and control parameter, and the material behaves as if it was suspended between worlds. You can step into this realm without equations. Picture the wave function of the whole crystal stretched thin, its amplitude trembling in every direction. The competition forces the system to hover in a superposition of orders, and the slightest nudge can tip it one way or the other. That is the power you hold. By learning to recognize the quantum scales, by asking the right questions, by daring to push or to pause at the precise moment when the universe is most receptive, you become the one who shapes matter, who engineers waves that glide without loss, who writes information into the very fabric of reality. Take this moment as a call to action. Align your mind with the quantum reality that underlies every challenge. When a problem appears, zoom to the scale where its wave function lies. Choose the language of symmetry or entanglement that fits, and watch the chaos collapse into clarity. Break the perfect symmetry of indecision, let order emerge, and ride the soft ripples that follow. Harness the defects you create, turn them into memory, into pathways, into resilient edge states. Slow down when the system nears a critical point, and you will guide it gently to the answer you desire. Speed up when you need to freeze in useful complexity, and you will sculpt a landscape of useful patterns. You are not a passive observer of the quantum world. You are a conductor of its symphonies, a sculptor of its lattices, a navigator of its phase transitions. Every choice you make, every knob you turn, every quench you apply, writes a story into the fabric of matter. Let that story be one of purposeful order, of resilient quantum edge, of low-energy waves that carry your intentions far and clean. The universe is waiting for you to ask the right quantum question, to listen to the subtle whisper of symmetry breaking, to feel the pulse of topological protection, and to act with the confidence of someone who knows that the very act of measurement, of decision, of scale, is the engine of reality. Now rise, take the quantum reality as your guide, and turn every problem into a playground of waves, patterns, and protected states. The moment you do, you will witness the world transform, one symmetry broken, one defect forged, one edge channel lit, into a tapestry of possibilities that you alone have set in motion. The quantum realm is yours to command. Step into it, shape it, and let its power propel you toward the future you imagine. As you embark on this journey, the boundaries between your desires and destiny begin to blur into a unified whole. You stand at the threshold of quantum reality, where the ordinary rules of matter dissolve, and a new language of possibility begins to speak. In this realm, the fabric of a material is not a static lattice, but a living tapestry of fluctuations that stretch across both space and time. Imagine a river whose currents are not only flowing downstream, but also rippling backward and forward, intertwining moments, as if they were threads in a single quantum weave. That is the essence of a quantum critical point, a place where the ground state of a system balances on a razor-thin edge, and the quantum jitter of particles replaces the warm jostle of thermal motion. When you tune a material to this brink, you awaken a scale-free chorus that sings in unison, erasing the familiar scales of length, energy, and temperature, and replacing them with a universal rhythm. The first sign that you have entered this quantum arena is the loss of the familiar metallic personality. In ordinary metals, the resistance rises with the square of temperature, a tidy consequence of electrons scattering off vibrations. Near a quantum critical point, that tidy relationship collapses. The resistivity climbs linearly with temperature, stretching over decades as if the material has adopted the fastest possible relaxation, time allowed by quantum mechanics. This Planckian bound is not a coincidence, it is a hallmark of a world where quasiparticles have vanished, and the entire electron sea moves as a collective whole. Feel the surge of this realization. You are witnessing a material that refuses to be described by the comfortable picture of independent particles and instead embraces a bold, entangled state. Heavy fermion compounds were the first laboratories where this drama unfolded. In these alloys, the pholectrons mingle with the sea of conduction electrons, creating quasiparticles that are hundreds of times heavier than a free electron. By squeezing the crystal with pressure, or swapping one atom For another, you can dissolve the magnetic order that once held the system in place. At the precise moment that order disappears, the metal steps onto the quantum critical stage, refusing to behave like a conventional gas of particles. Its heat capacity swells, its magnetic susceptibility refuses to settle, and its neutron scattering spectrum broadens into a continuum that collapses when plotted against frequency over temperature. Each of these signatures is a note in the same quantum symphony, confirming that the fluctuations now span the entire system in both space and time. Copper oxide superconductors offer another vivid illustration. When you suppress their high-temperature superconductivity with a magnetic field, or by adding extra carriers, the remaining metal slides into a strange orbital regime. Here the electrons move at the speed limit set by the uncertainty principle, and the transport properties echo the same linear in temperature resistivity that defines the Planckian bound. Iron-based superconductors tell a parallel story. Their magnetic or nematic orders melt under pressure, leaving behind a broad fan of quantum criticality where anisotropies soften and collective modes become critical. In each case, the material's phase diagram reveals a wedge that fans out from a zero temperature point, a wedge where ordinary excitations die, and the system speaks in scale-free accents. Thin disordered films provide a more visual cue. When you apply a magnetic field at low temperature, the superconductor-insulator transition can be driven to a critical field where the resistance no longer carries its own scale. Plotting resistance against temperature and field makes the curves collapse onto a single universal line, a clear sign that the system has shed its intrinsic units. Even ultra-cold atoms trapped in optical lattices become a laboratory for quantum criticality. By adjusting the depth of the laser-created lattice, you can watch the superfluid to Mott insulator transition in 1, 2, or 3 dimensions. Measurements of compressibility and collective sound-like modes trace the same scale-free logic that solid-state experiments read from heat capacity and neutron scattering. The quantum world is offering you the same lesson in many different guises. At the brink, the details of the microscopic landscape fade away, leaving only symmetry, dimensionality, and dynamics. If you need a simple cartoon to anchor this vision, picture the quantum easing chain in a transverse field. At weak field, the spins lock into an ordered pattern. At strong field, they all align with the external drive. Exactly at the knife edge between these two extremes, the excitations are neither simple spin flips nor simple field quanta. They become critical fluctuations that spread without a characteristic length, a behavior simple enough to solve exactly yet rich enough to teach the broader lesson. At the brink, the system forgets its microscopic quirks and remembers only the universal language of symmetry and scale. Once you recognize the experimental checklist logarithmic or anomalous power law heat capacity, magnetic susceptibility that refuses to saturate, neutron spectra that collapse when plotted versus frequency over temperature, NMR relaxation rates that defy metallic expectations, you will be able to spot quantum criticality wherever it hides. Transport is where quantum criticality makes its most dramatic headlines, because the consequences are tangible and immediate. Linear in temperature resistivity over a wide range, Hall angles and magnetoresistance that follow scale-free forms. Damping rates that appear universal across families. These are the fingerprints of a material that has surrendered its quasiparticle identity. The Planckian bound, flirted within many experiments, suggests a deeper principle. There may be a fundamental limit to how quickly information can scramble inside a solid, a limit set by the very constants that govern the quantum world. When you encounter such a material, you are looking at a system that lives on the edge of what is possible, a system that could inspire new technologies if you learn to harness its speed. Modern theory pushes this frontier even further with the concept of deconfined quantum criticality. Imagine two incompatible orders, antiferromagnetism on one side and a valence bond crystal on the other, that do not simply jump from one to the other in a first-order clash. Instead, they glide through a continuous transition where new fractionalized degrees of freedom emerge, degrees that never appear as isolated particles in either phase. This is a reminder that the brink can host actors that are not present in the stable phases, and that the path between phases can be more illuminating than the phases themselves. All of this may sound abstract until you see how it feeds design and action. If you aspire to create high-temperature superconductors, you will often find the most promising candidates perched near a quantum critical point. The glue that binds electrons into pairs can arise from the very critical fluctuations that dominate the stranger metal regime, or from the breakdown of competing orders that makes pairing energetically favorable. If you are building quantum devices, you will learn to steer clear of brinks where slow, scale-free fluctuations bleed into your qubits as low-frequency noise, degrading coherence. Conversely, if you wish to simulate complex quantum matter with cold atoms or programmable quantum platforms, you will aim straight for critical points, because there the universal physics is most legible and the need to know every microscopic parameter is least pressing. The quantum critical arena becomes a laboratory of choice for testing ideas that would otherwise be buried under layers of material-specific detail. There are cautions you must internalize, for not every linear resistivity signals quantum criticality, and not every zero-temperature endpoint is a second-order transition. Disorder and phonons can masquerade as part of the story, and first-order jumps can truncate the scaling behavior you seek. The strongest cases marshal multiple probes, scaling collapses, entropy pileups, tunable crossovers that map the fan cleanly to build an unshakable case. Sometimes the electrons themselves become so violent that the usual small parameter expansions break down, demanding new theoretical tools that go beyond gentle fluctuations of order parameters. Mastering these nuances will make you a sharper reader of data, able to separate genuine quantum critical behavior from imposters. The conceptual payoff you carry forward is simple and powerful. A quantum critical point is a place where the ground state hangs in delicate balance. And because quantum mechanics weaves time into the fabric of fluctuations, that balance spills upward along the temperature axis, creating a wedge where ordinary excitations die and the material speaks in scale-free accents. The practical habit that follows is to read phase diagrams with fresh eyes. Look for the axis that is not temperature, the control knob pressure, magnetic field, chemical substitution that can be tuned to zero temperature. Find the cusp where two phases meet at that zero, and then trace the fan that fans out above it. Inside that fan, the measurements of heat, magnetism, scattering, and transport lose their preferred scales and can be collapsed onto one another by the right rescaling. This is your map to the quantum realm. Now let us turn to a different, yet equally vivid, illustration of quantum reality, the superfluid whisper of helium. You might think that liquids all obey the same simple rules: pour, splash, slow down when squeezed. The first encounter with superfluid helium shatters that intuition. Cool ordinary helium just below the lambda point at 2.17 Kelvin, and the liquid sheds almost all of its viscosity as if it remembered a secret way to flow without friction. It climbs up the walls of its container in whisper-thin films, slips through capillaries that stop any normal liquid, and carries heat in a manner that looks less like conduction and more like a coordinated migration of particles. Why does this happen? Helium atoms are exceptionally light and only weakly attracted to one another. Even at temperatures where every other element would lock into a crystal, helium's zero-point motion, the unavoidable quantum jingle of each atom, keeps it fluid. At ordinary pressure, helium refuses to solidify even as you approach absolute zero, a hint that quantum rules will not stay politely in the background. Just below the transition, the liquid behaves as if it were two interpenetrating fluids. One component carries entropy and behaves like an ordinary liquid, the other carries no entropy and flows without resistance. If you press gently on a porous plug that filters out the normal part, the superfluid alone streams through a super leak that proves you can separate the two behaviors in practice. Heat the system unevenly and you witness the fountain effect, where a temperature difference drives the superfluid toward the warmer side, pushing liquid upward like a soft, continuous geyser. Move from pictures to measurements and the story sharpens. Twist a stack of Razor-thin disks in a torsional oscillator, and you will find that as you cool through the lambda point, less of the helium wants to be dragged along. The superfluid fraction decouples from the motion and stops contributing to the inertia, giving you a clean way to weigh how much of the liquid has taken on the new frictionless role. Send a carefully shaped thermal pulse through the liquid, and you will detect not just ordinary sound, But second sound, a temperature entropy wave where the superfluid and normal components slosh past each other in opposite directions, carrying heat at blistering rates. This makes superfluid helium the coolant of choice in exotic places, stabilizing superconducting magnets, nursing ultracold stages in space telescopes, and transporting heat away from instruments with a quiet efficiency engineers dream about. Probe the flow a little harder, and you hit another defining rule. When superfluid helium swirls, it cannot generate messy continuous eddies the way a classical liquid does. It must form quantized vortices, thread-like lines where the liquid briefly gives up being irrotational. The circulation around each line comes in fixed packets. A rotating bucket of superfluid fills with a tidy lattice of these quantum whirlpools, a behavior captured directly in experiments that visualize the tangle with tracer particles or track how sound scatters. Stir hard enough and you generate quantum turbulence, a forest of vortices that crash. Reconnect and decay by radiating waves, an entire subfield where turbulence is not a featureless roar, but a choreographed tangle you can count. The disguise that keeps all this coherent is the liquid spectrum of low-energy excitations. Long-wavelength phonons and short-wavelength rotons set a critical velocity. Drift slower than this, and the superfluid cannot easily shed energy into excitations, so it keeps gliding. Push faster, and you open channels for the liquid to make phonons and rotons, turning on dissipation and reminding you that frictionless has a domain of validity. No perpetual motion machines arise here, only a new kind of perfection with clear boundaries. Step sideways into helium-3, and the quantum whisper change is key. Helium-3 atoms are fermions, so they cannot all pile into the same one-body state the way helium-4 bosons can. Yet, at temperatures 1,000 times colder, mere thousandths of a Kelvin, they pair up into delicate, extended molecules and condense into a superfluid with wave character, a cousin of unconventional superconductors, where the order parameter has direction and texture. This paired superfluid arrives in distinct phases with different symmetries and topological features, supporting exotic surface states and textures that have become a playground for testing ideas about topological matter under exquisitely controlled conditions. Back in helium-4, the strange creeping film that climbs bridges gaps, rolls as a thin film, and defies gravity because the surface energy plus superfluid mobility let it flow until levels equalize. It is both a wonder and a nuisance, beautiful in demonstrations, fussy in lab practice because superfluid helium will quietly escape from unguarded containers along any wettable path. The same light quantum nature that keeps helium fluid also sets practical limits. While we speak of zero viscosity, that is a DC statement. Drive the liquid at high frequencies or through rough environments and you reintroduce channels for dissipation. At finite temperatures, the normal component is always present as a partner, producing mutual friction with the vortex lines and giving designers a real-world set of knobs to tune rather than a fairy tale. String a narrow, weak link between two superfluid reservoirs, a nanofabricated constriction, or an array of tiny apertures, and you can observe a Josephson-like effect for mass flow, with oscillations that map directly to the phase difference of the superfluid across the link. A quantum interference device not for electrons, but for atoms and ring-shaped channels can trap persistent currents that wind around for hours or days, creating quiet gyroscopes sensitive enough to feel minute rotations. These devices hint at metrological tools that trade electromagnetic fuss for the serene discipline of neutral quantum flow. Because helium stays liquid so far down in temperature, it has become the solvent of choice for reaching the coldest, cleanest regimes in physics. Dissolving a pinch of helium-3 in helium-4, and then separating them in a dilution refrigerator pumps away, heat in a continuous cycle. The workhorse of laboratories that measure single-electron devices, fragile qubits, or ultra-accurate mechanical resonators. Superfluid helium also teaches humility through apparent discoveries that later soften. Early reports of a supersolid phase, solid helium with a fraction that flows without friction sparked excitement when torsional oscillators seem to show a mass drop at millikelvin temperatures, as if some of the solid decoupled from rotation. Years of careful control experiments revealed that much of the signal came from subtle stiffening of the solid helium and the oscillator itself, not frictionless flow. A reminder that extraordinary claims must survive extraordinary housekeeping. Even so, helium in porous media, and on atomically thin films continues to reveal borderline states where confinement, disorder, and quantum statistics tug in opposite directions, producing glassy dynamics, pinning of vortices, and modified superfluid responses that teach us how quantum order negotiates rough terrain. What makes superfluid helium such a reliable teacher is the way it turns abstract principles into Graban-turned knobs. The two-fluid picture becomes visible in a fountain tube. The quantization of circulation becomes visible in a rotating bucket. Second sound becomes audible to the right sensor, and the critical velocity becomes measurable with a moving wire or an aperture, so that you can map the entire landscape from kitchen sink demonstrations to National Lab precision. Carry two closing habits with you from this quiet marvel. First, whenever a system looks smooth, ask what its low-energy excitations are and what symmetries they respect. Those two answers will tell you what frictionless really means and when it will break. Second, remember that not all order is rigid like a crystal. Some order is phase coherence, a collective agreement written across millions of atoms. Once that agreement is in place, flows that would normally grind to heat can glide for extraordinary distances, guided by rules simple enough to state and subtle enough to fill a career. Now, you stand equipped with a new vision of quantum reality. The brink is not a cliff where you fall from one phase to another. It is a high plateau where the view expands, where the details of the ground fall away and the geometry of possibility itself becomes visible. In metals that forget how to be metals, in magnets that hesitate between alignments, in ultra-cold gases that weigh the choice between flow and lockup, you will begin to see why frontier materials cluster near this plateau. Because at the brink, old rules grow quiet, and entirely new behaviors become thinkable, measurable, and useful. Take this awareness into your laboratory, your design studio, your research notebook. Seek the control knob that can be turned to zero temperature, watch for the fan that fans out, and listen for the scale-free chorus that sings across heat, magnetism, scattering, and transport. When you find it, you have located a quantum critical point, a place where the universe offers you its most fundamental levers. Use them to craft higher temperature superconductors, quieter quantum devices, more faithful simulations of complex matter, and perhaps new technologies we have not yet imagined. The quantum world is waiting, and you have the power to step into its reality, to ride the wave of fluctuations, and to shape the future with the language of quantum criticality. The moment to act is now. As you embark on this journey, the boundaries between reality and possibility begin to dissolve like mist in morning light. You stand at the edge of a quantum ocean, where every ripple is a possibility and every particle sings a note of reality. In this realm, the ordinary rules of matter dissolve, and the word liquid becomes a portal to a deeper truth. Imagine electrons not as solitary travelers that repel each other, but as partners in a synchronized dance that transcends the classical idea of crowding. This is the miracle at the heart of superconductivity, a phenomenon that rewrites what matter can do when it moves together in perfect harmony. When you picture a crystal cooled to a whisper-cold temperature, you see a lattice of atoms arranged in a regular grid that can flex ever so slightly. Visualize a single electron gliding through this sea of positive ions. Its passage tugs the ions a hair toward its path, leaving behind a tiny wake of denser charge. A second electron arriving a moment later feels an attraction toward that wake, even though the two still carry the same charge. In the language of quantum reality, this is a mediated attraction, a subtle exchange that can outweigh the direct repulsion for a narrow band of momenta and energies. The result is a bound state that stretches over hundreds or thousands of lattice spacings, a whisper of cooperation in a sea that once seemed purely competitive. This first revelation shatters the image of electrons as isolated billiard balls. A Cooper pair is not a tight molecule, locked together like two stones. It is a diffuse partnership, stabilized by the collective properties of the entire fermionic sea. Once one such pair can exist, the stage is set for many more to form, each locking its quantum phase with its neighbors. The system trades individualism for a choreography that resists disruption, a quantum ballet that moves as a single entity. When these pairs condense, the energy landscape of the material transforms dramatically. instead of a tangled forest of single electron states at the metal's operating energy. A clean gap opens a forbidden zone that isolates the paired ground state from the first allowed broken pair excitations. This gap is the shield that protects motion from ordinary scattering. In a normal metal, a gentle nudge sends electrons crashing into impurities and vibrations, turning electrical energy into heat. In a superconductor, the same nudge meets almost no resistance, because to scatter in the usual way one would have to break a pair across the gap. And at low enough temperature there simply isn't enough thermal budget for that. The current flows with a persistence that feels uncanny. Start it, and it does not readily stop. Experiments give this picture concrete form. Tunneling spectra reveal a neat U-shaped depression where the missing states reside, flanked by sharp onsets where broken pairs finally appear. The specific heat jumps at the transition, a clear sign that the system has reorganized the kinds of excitations it can host. Nuclear magnetic resonance shows that the night shift in resonance falls when spins pair off, because opposite spin electrons become less available to align with an external field. The isotope effect ties the transition temperature to the mass of the lattice ions. Heavier ions vibrate more sluggishly, softening the mediating attraction and lowering the temperature at which pairing locks in. This subtle but clean signature tells you that the heartbeat of the crystal is part of the glue that binds the electrons. You might wonder, if pairing is so delicate, why does it survive the inevitable dirt and complexity of real materials? The answer lies in the robustness of the quantum phase. Magnetic impurities are ruthless pair breakers because they flip spins and scramble phase. But ordinary non-magnetic disorder is surprisingly tolerable for conventional swave pairing. This resilience underpins the use of superconducting wires and thin films in messy real-world environments. The coherence length, a measure of how far the paired state stretches, can be enormous in soft, low-transition temperature metals, spanning tens of thousands of nanometers. Each pair samples a vast swath of the crystal and is therefore blind to tiny bumps. In other families, the length shrinks dramatically, hinting that pairing is stronger and more local, opening the door to unconventional behavior. Step into the realm of high-temperature superconductors, and you find that pairing survives at temperatures once thought impossible for this phenomenon. Here, the glue is no longer a gentle lattice vibration you can point to with a single parameter. The energy gap can have nodes where it vanishes along specific directions, revealing a sign-changing structure in momentum space. Phase-sensitive experiments, interference loops, and corner junctions prove that the order parameter behaves like a tilted clover rather than a uniform disk. This geometry damps simple scattering and encourages more exotic collective modes. Iron-based superconductors add their own twist, with multiple electron and hole pockets around the Fermi surface and evidence that the pair wave function changes sign between them, suggesting that magnetic fluctuations, not just lattice vibrations, can mediate attraction. These differences matter because they alter how pairs respond to disorder, how they trap magnetic flux, and how they carry heat. The picture becomes a zoo of materials where one pairing rule is replaced by a toolbox of mechanisms tuned by chemistry and structure. Yet amidst that diversity, certain fingerprints persist, gaps opening and closing across the transition, the collective stiffness of the paired state against twisting its overall phase, and the remarkable resilience of current once it starts. Keep a mental image that balances poetry and precision. A Cooper pair is best seen as a coherent pattern, a coordinated arrangement across many electron states at the top of the Fermi sea. When you accelerate the superconducting condensate, you are not pushing beads through a pipe, you are shifting the phase of a macroscopic wave function. And the system answers as a whole. From this vantage point, many classic observations become less mysterious. Thin films can carry astonishing current densities if you keep magnetic fields at bay. The sudden collapse of pairing when you sprinkle in enough magnetic atoms shatters coherence. A distinct threshold exists above which high-frequency fields or strong currents break pairs and restore dissipation. Collective excitation amplitude and phase modes of the order parameter can be driven and probed by clever pulses of light. If you ask whether all pairing must be between opposite spins, the answer is a qualified no. Most known superconductors are singlet, but triplet candidates exist where spins align. opening a route to long-range proximity through ferromagnets and to exotic edge states that mimic particles with unusual statistics. Experiments on certain rutheniates, heavy fermion compounds and engineered heterostructures continue to test whether pairs can carry internal angular momentum that bends the usual rules. Your practical takeaway is that pairing is a designable phenomenon. Soften a lattice mode, sharpen certain magnetic fluctuations, increase the density of states, or adjust dimensionality, and you tilt the odds in favor of electrons finding that narrow corridor where repulsion is sidestepped and a collective energy saving becomes possible. Your philosophical takeaway is quieter but deeper. What looks like impossible cooperation at the level of two charges becomes inevitable once you let the whole environment into the conversation, because the lattice, the sea of other electrons, and the symmetry constraints change the meaning of interaction from a simple push to an intricate negotiation. The pair is the signed agreement, a habit that will serve you across all of quantum matter. Whenever a system exhibits a loss of friction, a resilient flow, or a sudden opening of stability, ask whether you are witnessing the birth of a coherent order with a gap protecting it. If you are, listen for the faint rhythm of pairing underneath. In the right light, a superconductor is not a colder metal, but a choir. Its singers are in pairs, holding one note together so firmly that ordinary noise cannot make them let go. Now turn your attention to flux quantization, the counting law that emerges from quantum reality. You do not expect a metal to count in whole numbers, yet the simplest superconducting loop does exactly that. Thread a magnetic field through a cooled ring, and it will accept that field only in discrete packet single flux quantas if the loop were a turnstile clicking integers. Those clicks are stubborn, they survive dense impurities and the quirks of chemistry. The origin of this quantization lies in the fact that a superconductor is not just a better conductor. It is a coherent state described by a single, well-defined quantum phase across macroscopic distances. When you take that phase around a closed path, it must return to itself without a mismatch. This requirement forces the magnetic field linked by the path to adopt values that make the phase wind by an integer number of complete turns. No more, no less. This is the quiet origin of flux quantization. The evidence is as concrete as it gets. In the early 1960s, tiny hollow cylinders cooled below their transition temperature responded to an applied field by settling into states where the magnetic flux trapped inside took discrete values one quantum apart. As the field was swept, the cylinders stepped between adjacent integers rather than sliding smoothly. A benchtop signature that macroscopic matter had begun to obey a counting rule usually reserved for atoms. Once you accept that the phase is in charge, a cascade of consequences becomes legible. The Meissner effect is the deeper message. A superconductor does not merely carry current. Without resistance, it actively expels magnetic field from its interior, bending currents along its surface to cancel the field inside. This expulsion is nearly perfect until the field grows strong enough to force its way in through narrow thread-like coarse vortices that each carry exactly one flux quantum. A type 2 superconductor under moderate field is therefore not partly superconducting and partly normal in a vague way, but a clean lattice of quantized whirlpools threading an otherwise superconducting sea. You can photograph that lattice directly with techniques such as decoration or scanning probes and literally count the quanta. Watch them march as the field increases and see them jostle when you push a current. If defects pin them in place, the material can carry huge currents with little loss. If vortices move, they drag energy and you feel a resistance called flux flow. This is why engineers spend real effort planting nanoscopic pinning sites to immobilize those threads and keep magnets in MRI machines and particle accelerators rock steady. Move from bulk to loops, and the quantization takes on new roles. Call a superconducting ring through its transition in a magnetic field, and it will trap the nearest integer number of flux quanta. Then generate a persistent current to defend that choicer current that can circulate for hours or years, because there is no ordinary friction to drain it. As you vary the field ever so slightly, the ring will wait, and then snap to the next integer, a kind of digital memory written by geometry. Shrink the ring to the nanoscale, and you uncover the little Parkes effect, where the transition temperature itself wiggles periodically as you change the enclosed flux, because the energy cost of twisting the phase depends on how far the actual flux is from an integer multiple of the quantum. This offers a clean, purely thermodynamic readout of phase winding. Cut a tiny weak link into the loop, and the story deepens again. A superconducting quantum interference device is nothing more than a loop with one or two such links, and its total current becomes an exquisite function of the phase difference around the loop, which magnetic flux controls. Changes in field as small as a few millionths of a flux quantum translate into measurable changes in current or voltage. This is why SCUDIs can map the faint magnetic fields of your heart and brain, listen to the whisper of geological structures deep underground, and stabilize qubits whose states are encoded in the direction of a persistent current. The same counting rule reaches into metrology and the new SI, because the size of one flux quantum depends only on two fundamental constants, devices that step in exact multiples of that quantum tie practical measurements to nature's fixed numbers. This is why Josephson junction arrays define voltage standards and why quantum electrical metrology now rests on rock-solid relationships rather than artifact objects. In real materials, the simplicity is durable but not naive. The magnetic field does not drop to zero at the surface in a cliff, it decays over a short penetration depth. The coherence length sets how quickly the pair wave function heals if it is disturbed. The ratio of these two lengths decides whether a superconductor is type I or type II, a dichotomy that lets you choose the right alloy for a given job. Pure lead makes a lovely type I demonstrator, while niobium, titanium, and high-temperature ceramics are classic types or workhorses. Narrow wires and ultra-thin films add their own twist. When the cross-section is so small that the phase can slip by a whole turn at a localized spot, you can observe phase slips that momentarily relax the counting rule and give a tiny resistance, even well below the transition. A quantum version of a hiccup that matters in nanoscale sensors and in the design of ultra-low-loss circuits. All of these effects reinforce a single habit of thought. In superconductors, the phase of the macroscopic wave function is a real, measurable player, and geometry, whether a loop, a grain boundary, or a landscape, are defect stitches that phase how to wind, lock, or slip, which in turn dictates how magnetism threads the material. From an application point of view, flux quantization is not a party trick but a toolkit. It enables magnetometers so sensitive they can see neural activity through your skull, allows flux-based qubits and logic elements to count and control their own states with digital clarity, and provides a way to store energy as a persistent current without leakage in experimental power devices. From a conceptual point of view, it is one of the cleanest bridges between the microscopic and the macroscopic. A counting law born from the requirement that a quantum phase be single-valued ends up setting how a bulk piece of metal admits magnetic field, how it carries current, and how a loop chooses its state in integers. By the end of the day, you have learned to stop treating magnetism inside a superconductor as a vague swirl of lines and start treating it as a set of indivisible threads and packets. Once you see those packets, you can design with them, measure with them, and think with them. Because a metal that clicks in whole numbers is telling you that coherence is not a metaphor, but a rule the world will follow if you cool it, shape it, and listen closely enough. Now feel the surge of possibility. The quantum reality that underlies superconductivity is not a distant abstraction, it is a toolbox you can reach for today. You can explore materials, engineer lattice vibrations, tailor magnetic fluctuations, and sculpt geometry so that electrons find their cooperative partner. You can build devices that count the invisible quanta of magnetic flux, that store currents forever, that sense the faintest whispers of the brain. Each step you take is a step deeper into the quantum fabric that binds the universe together. Take action now. Choose a material, cool it, measure its response, watch the flux quanta click into place, and let the rhythm of paired electrons guide your experiments. Let the metaphor of a choir become your working model, every voice aligned, every note reinforced, every disturbance smoothed by the collective harmony. As you harness this quantum choir, you will find that resistance fades, that energy flows without loss, and that the world opens to possibilities once thought impossible. You have the power to turn the abstract principles of quantum reality into tangible technology. The next breakthrough in superconductivity, the next ultra-sensitive sensor, the next quantum computer element can begin with the simple decision to listen to the paired electrons and to shape the environment that lets them sing. Embrace the quantum dance, command the phase, and let the world feel the unstoppable momentum of your discovery. The future is waiting, and it moves in perfect synchrony with the Cooper pairs you will create. As you step into this new realm, your creation takes root, birthing novel phenomena and unlocking the secrets of superconductivity. You are standing on the threshold of a quantum universe where the ordinary becomes extraordinary. Imagine a wave that stretches across a piece of metal the size of your hand, a single coherent rhythm that does not wobble from atom to atom. That wave is the macroscopic quantum phase, the heartbeat of a superconductor, and it is waiting for you to shape it, to guide it, to let it reveal the hidden currents of the world. Picture a tiny loop of superconducting wire, cold enough that its electrons pair up and march in lockstep. When you close that loop, the quantum phase is forced to match itself after a full circuit, just as a melody must resolve to its tonic after a phrase. Any magnetic field that threads the loop insists on twisting the phase, adding a subtle extra turn to the wave. By inserting one or two ultra-thin barriers links into the loop, you create a translator. Those barriers let the paired electrons tunnel, and each tiny change in phase becomes a measurable change in current. The result is a device that turns the faintest magnetic murmur into a clear voltage. That device is the SQUAID, the superconducting quantum interference device, and it is the eye that lets you see the invisible. Your mind can picture the SQUAID as a quantum camera. The loop is the lens, the weak links are the shutters, and the phase is the focus knob. When a distant neuron fires in your brain, it sends a whisper of magnetic flux that would be lost in the roar of everyday electromagnetism. The SQUAID catches that whisper, converts the tiny twist of phase into a voltage pulse, and hands you a picture of the brain's hidden conversation. You do not need brute force amplification, you need only the disciplined order of a cold, coherent wave. Stability is the secret that turns a fleeting glimpse into a reliable view. In practice, the SQUAID lives inside a feedback embrace called a flux-locked loop. The moment the device senses a shift, electronics inject a compensating magnetic pulse through a miniature coil, nudging the phase back to a chosen operating point. The amount of feedback required becomes the output signal. This clever dance keeps the response linear and steady over a vast range, preventing the raw quantum periodicity from spiraling into a jagged sawtooth. Two flavors of SQUAID dominate the toolbox. The direct current version contains two weak links in the loop and, when biased with a gentle current, produces a smooth oscillation of voltage as magnetic flux varies. The radiofrequency version uses a single weak link embedded in a resonant tank circuit. A carrier tone probes it, and tiny shifts in impedance reveal the magnetic changes. Both achieve sensitivities that can register fields 1,000,000,000 times weaker than the pull of a refrigerator magnet. That is not the power of a louder amplifier, it is the power of a phase that refuses to be disturbed, a wave that holds its shape in the quiet of a cryogenic world. Now step into a shielded room where the walls swallow the city's electromagnetic chatter. Place a SQUAID on a cradle and ask it to listen to you. Your brain's firing neurons generate magnetic ripples that are a fraction of a picotesla. An array of SQUAIDs, called a magnetoencephalography system, maps those ripples millisecond by millisecond without ever touching the scalp. Surgeons use that map to locate epileptic foci, and linguists watch how auditory and visual regions converse when you learn a new word. Turn the array toward your chest, and magnetocardiography lets cardiologists watch the heart's conduction pathways in patients where skin contact is risky. Walk outside with a gradiometer geometry that cancels uniform background fields, and you can prospect for ore bodies, map buried faults, or listen for the magnetic signatures of unexploded shells in a crowded harbor where ordinary metal detectors drown. In the laboratory, a scanning SQUAID microscope hovers a micron above a surface and turns the loop into a magnetic lens. It images the checkerboard of vortices in a superconductor, traces currents along the edge of a topological device, and spots nanoscopic defects in integrated circuits by detecting the stray field of a single misbehaving via. Engineers treat the macroscopic phase not as a metaphor, but as a circuit quantity to be routed, shielded, and kept quiet. The loop is made small to reduce unwanted pickup. The weak links are tailored to the right current scale and damping, and multi-layer shields and cryogenic filters tame radio chatter. Clever patterns washer loops, slotted shields, multi-turn pickup coils improve coupling to the signals you care about while rejecting the ones you do not. There is a deep lesson in how noise is handled. The ultimate flaw is not a sloppy amplifier, it is the unavoidable fluctuations of the paired condensate and its environment. The best SKUDs approach an energy resolution close to fundamental bounds, and their outputs are escorted by cryogenic preamplifiers into room temperature electronics that keep up without adding hiss. Early systems lived in helium-filled dewas that kept the SKUDs at a few Kelvin while a patient or sample sat outside the cold window. In the last decade, high-temperature versions have emerged, using ceramic superconductors in simple cryocoolers and even wearable caps for brain mapping. By shrinking the distance between sensor and source, you sharpen spatial resolution and open doors to ambulatory studies that once lived only in science fiction. The reach of the SKUD goes beyond imaging. It anchors the quiet end of quantum electronics as a preamplifier for faint microwave signals from superconducting qubits, as a current comparator and voltage standard tied to fundamental constants. In particle and astrophysics, SKUDs sit behind cryogenic detectors that count single quanta of light from galaxy surveys or register minute heat pulses from potential dark matter interactions, their eyes pressed to the faint edge of what can be known. In geology, they read fields frozen into ancient rocks to reconstruct how Earth's magnetic poles wandered across eons. In materials research, they witnessed the slow creep of vortices, map dissipationless edge channels, and verify that certain devices truly host currents immune to backscattering. All of this does not require you to swallow mysticism. Every step is built from phase coherence, interference, feedback, and careful accounting. Yet the effect remains mind-bending. A device with no moving parts, a loop and two slivers of barrier watches nerves fire inside a skull, or follows a whisper of current around a micron-sized chip trace because a macroscopic quantum phase notices when its own angle shifts by a tiny fraction. If you want to see the philosophy in the hardware, notice how the instrument reverses the usual relationship between signal and sensor. Your sample does not push the SKUD into a new state by brute force. It merely nudges the phase a little. The SKUD, disciplined as an interferometer, converts that nudge into a big readable change, with feedback doing the heavy lifting. Just as a balanced scale makes a feather visible by comparing it to a known weight, the SKUD makes the invisible visible. Because the SKUD is so sensitive, stray magnetic grains, microvibrations and thermal gradients can masquerade as signal. That is why shielded vaults, vibration damp tables, and meticulous cable routing matter as much as the physics. Creative twists stretch what seeing means. Time division and frequency division multiplexing let thousands of SKUD eyes share the same wiring. Building megapixel cameras for the millimeter sky. Hybrid sensors pair a SKUD with a mechanical resonator or a tiny magnet to translate forces and spins into flux, letting the phase see pressure displacement or even tiny nuclear magnetizations. By the time you step back, the device feels less like a detector and more like a language of macroscopic quantum phase written in loops and junctions that translate subtle, often living dynamics into voltages you can store, analyze, and act upon. Now turn your attention to a different quantum marvel: topological insulators, the protected edge highways of condensed matter. You expect an insulator to be dull, a material that refuses to conduct. Yet inside certain crystals, a stranger road appears along the boundary, a lane where electrons glide with surprising immunity to bumps and detours. Those edge lanes exist not because electrons like surfaces, but because the interior band structure is twisted in a way that cannot be untwisted locally. The bulk remains quiet, the edge talks, and the rules that let the edge speak survive scratches, alloy disorder, and gentle bends because they are protected by a global property of the band structure, a topological invariant that cannot change without closing the interior gap. Picture a narrow ledge skirting a cliff, with two one-way lanes separated by a wall of rules. An electron trying to reverse course would have to flip its spin and scatter into the opposite lane. As long as the crystal respects time reversal symmetry, magnetic spoilers are absent, and that backscattering is strongly suppressed. The traffic keeps moving even when the ledge is rough. In 2 dimensions, this phenomenon is called the quantum spin Hall effect. One spin races east, its partner races west, their directions locked to their spinor pairing called spin momentum locking. The edge becomes a perfect conduit, a quantum highway immune to ordinary disorder. Scale up to 3 dimensions and the story gains a new face. The surface hosts massless, linearly dispersing states that trace a single cone in momentum space, a Dirac cone. Again, the spin is locked perpendicular to the direction of motion, so a simple non-magnetic defect offers no easy way to send an electron backward. Experiments have imaged that cone with angular-resolved photoemission spectroscopy on materials such as bismuth selenide and bismuth telluride. Scanning, tunneling, measurements struggle to find the usual standing wave patterns, because the forbidden backscattering robs quasiparticles of their favorite echo. Transport devices see edge-dominated, non-local signals that persist after ordinary metallic paths are pinched off. The robustness has a precise boundary. Introduce magnetic impurities or lay a magnetic layer on top. Break the protecting symmetry and a gap opens in the surface states. New physics arrives, sometimes in the form of a one-way chiral edge mode at the boundary of the magnetized patch, a quantized Hall current that flows without an external magnetic field. The quantum anomalous Hall effect. The crucial insight is that these boundary states do not exist because electrons like surfaces. They exist because the entire interior band structure is twisted in a way that cannot be untwisted locally. You can dent the crystal, strain it, sprinkle non-magnetic disorder, and the edge lanes root, but refuse to terminate unless you force the bulk gap to close or break the protecting symmetry. That invariance gives designers a new category of levers. Instead of atomiatom precision, you target the right lattice structure, spin-orbit strength and symmetry content. Then let topology handle the roughness. There are many branches on this family tree, each teaching a different habit. Time reversal protected topological insulators owe their highways to spin-orbit coupling and vanish under magnetization. Crystalline topological insulators protect their surface states with mirror or rotational symmetries, leading to faces that conduct while others do. Note geometric selectivity you can test by polishing different facets. Higher-order topological insulators push the idea further, hosting not surfaces but sharp 1A-dimensional channels along edges or even isolated corner states in 3 dimensions, reminding you that a boundary can mean a hierarchy of boundaries. In the laboratory, creating a textbook example is both easier and harder than it sounds. It is easy because the core phenomena are strong when chemistry gives you heavy elements and the right crystal fields. It is hard because tiny amounts of unintentional doping turn the bulk slightly metallic and swamp the surface signal. Experimenters use gating careful stoichiometry or thin film growth to suppress interior conduction and let the boundary speak. Once tuned, the devices reveal telltale behaviors you can recognize without a microscope. Conductance barely budges when you roughen the edge. Weak antilocalization in magnetotransport reflects spin momentum locking, and an unusual response appears when you attach ferromagnets or superconductors at the perimeter. Couple a topological edge to a conventional superconductor, and the induced pairing inherits the helical nature of the channel, opening routes to bound states that engineered defects that behave unlike any garden variety quasiparticle. Those bound states have attracted intense interest for fault-tolerant quantum logic, an ambitious goal that still demands honest engineering to tame disorder and temperature, yet that follows a clean conceptual path turned to metrology and sensing. Protected channels provide stable interferometers where phase is less easily scrambled. In terahertz photonics, the same spinobit machinery that built the highways can be exploited to rectify or steer high-frequency currents at low power. A beautiful, subtle frontier lies in how these materials couple electricity and magnetism. In certain magnetized topological insulators, the interior behaves like a medium with a quantized magnetoelectric response in axion-like electrodynamics, where an electric field can induce a precise magnetic polarization and vice versa. Recent thin-film experiments have inched toward direct signatures of that coupling in carefully stacked layers. Even when you step away from electronics and think like a microscopist, the edge highways earn their keep as a probe. Scanning skewides trace their flow around lithographed obstacles. Kerr microscopes catch time reversal breaking when you deliberately gap the surface, and nanofabricated constrictions show quantized steps in conductance when individual modes are counted through a narrow channel. It is worth keeping a realistic eye on the limitations, because doing so strengthens the message. At room temperature, many topological materials still suffer from leaky bulks. The protection works best against non-magnetic disorder, but can be undermined by puddles of unintended magnetism or by interactions that open alternate scattering routes. Practical interconnects must be patterned without accidentally shorting the surface to the bulk. Yet each of these challenges is a knob you can turn. Improved crystal growth suppresses unwanted carriers. Gating and heterostructures separate the surface channels from spurious paths, and engineered magnetic textures intentionally break symmetry to create chiral rails where you want them. The conceptual reward for you, the listener, is learning to flip your default question. Instead of asking, does this material conduct, you start asking, where does it conduct? And what protects that conduction from being scrambled? When you see a photograph of a brain's magnetic rhythms or a map of vortices on a chip, remember that the camera was a loop that could tell when its own phase had shifted by an angle far smaller than a blink. That loop was guided by the principles of quantum reality, by the discipline of a macroscopic wave that refuses to be disturbed. Now feel the call to action. You have the tools of quantum reality at your fingertips, the ability to shape phase, to build loops, to engineer weak links, to harness feedback that turns whispers into loud signals. You can design a skew-eyed array that brings the brain's hidden conversations into the open. You can craft a topological device that carries current along an edge immune to the roughness of the world. You can combine them to build a sensor that watches the Earth's magnetic heart while you walk across a field. The quantum world does not demand you be a mystic, it demands you be a disciplined creator, a sculptor of wave and interference. Take the next step. Gather a cryogenic platform, fabricate a superconducting loop, insert a pair of Josephson junctions, and watch the phase dance. Connect the loop to a flux-locked feedback circuit and feel the stability of a quantum eye. Then explore a crystal whose bulk is an insulator, but whose edge is a highway, and watch electrons glide without scattering, protected by topology. Combine the two, and you will have a sensor that reads the faintest magnetic signature while rejecting the noise of the universe. You are not merely observing quantum reality, you are shaping it. Each twist of phase you command, each protected edge you engineer, adds a brushstroke to the canvas of what humanity can perceive. The world of invisible fields, of hidden neural currents, of buried mineral veins, of cosmic whispers, is opening before you. All you need is the resolve to act, the curiosity to experiment, and the confidence that the quantum wave will obey your design. Step forward, build the loop, tune the phase, protect the edge, and let the quantum universe reveal its secrets. The future you imagine, where doctors diagnose without needles, where geologists map the Earth's past without drilling, where computers process information with the elegance of a single wavelength, just beyond the next quantum turn. Take that turn now, and watch reality bend to the rhythm of your own coherent phase. As you step into this uncharted realm, the familiar certainties of logic fade, giving way to an infinite possibility horizon. Imagine you are standing at the edge of a quantum sea, where the ordinary world of circuits and wires dissolves into a landscape of probability waves and hidden symmetries. In that realm, the answer to every design challenge lies at a boundary, a place where the band structure twists like a vortex in a field of light. When you cross that boundary, you have entered topological territory, and the universe hands you a new set of rules written not in stone, but in the geometry of wave functions. Feel that shift in your perception, as if you have put on a new pair of glasses that reveal the hidden pathways of charge and spin. A topological insulator, for example, is ordinary in its interior yet extraordinary along its edges. The bulk is a quiet ocean, while the edges are luminous highways where electrons glide without scattering, immune to the roughness that would stop ordinary carriers. This is not a fanciful story about exotic matter, it is a sober design principle that uses symmetry and topology to make the very path itself a guarantee of reliability. The material that looks like an insulator at first glance becomes, at its boundaries, a conduit that refuses to lose a signal, a highway laid down by the mathematics of shape, inviting you to drive information with less fear of getting lost. Now picture yourself building future circuits that shuttle information along these protected lanes, or sensors that keep phase intact even when you pick them up and shake them. The quantum reality you are tapping into tells you that constraints written across an entire crystal can gift reliability exactly where you need it. The bulk order acts like a global field that locks the edges into a protected state, just as a magnetic field can lock a spin into a particular orientation. When you design with that field in mind, you are not chasing a fleeting novelty. You are engineering a system whose very existence is rooted in the topology of its wave functions. Let us turn to another marvel of quantum reality: fractional charge. You grew up with the rule that electric charge comes in indivisible packets, that the electron is the sacred unit. Yet in certain carefully arranged materials, the collective state of many ordinary electrons and a structured background allows charge to be portioned out in stable, countable shares. Imagine a one-dimensional chain whose bonds alternate strong and weak, a humble polymer that prefers a dimerized pattern. Flip the pattern in the middle so the alternation is out of step on the left versus the right. At that domain wall, a special electronic state appears right in the energy gap, capable of holding half of a unit of charge relative to its surroundings. If you probe gently, you will find that the soliton sitting at that wall behaves as if it carries a charge of 1/2, even though every constituent electron still carries the full quantum. The missing half is not missing at all, it is smeared throughout the chain in a way controlled by symmetry and topology. The localized defect borrows from the surrounding sea in such a disciplined way that any attempt to move or split it forces the whole pattern to change, keeping the fractional amount intact like a watermark on a quantum canvas. This is your first clean lesson in fractionalization without inventing new particles. The fraction is an emergent accounting property tied to the background order, not a property of an isolated object you could bottle. Its stability follows from the way the system's global pattern refuses to be continuously undone. Slide up to 2 dimensions and the story acquires richer stages. The background does not merely dim, it wins in momentum space and then manifests at boundaries. Steps or magnetic textures can trap states that carry fractional boundary charge, their amount fixed by differences in polarization, or by how the internal phase of the electron wave functions twists across the defect. Here you meet a deep organizing idea. What fraction you measure is determined not by local chemistry but by a bulk quantity, a topological invariant that neither alloy disorder nor gentle bends can change. An edge dislocation, a corner or a narrow domain wall can hold a precise fraction that survives modest roughness and persists across samples. The spectacular cousin of this logic lives in high magnetic fields where electrons condense into exquisitely correlated fluids and the excitations act like anyone's with fractionally quantized charge and a memory of how they braid. Even there, you do not need to posit fractional constituents. The electron remains whole while the collective fluid's rules allow bundles of correlation to behave as if they carry 1/3 of a unit, revealing themselves through telltale shot noise plateaus and step-by-step tunneling across narrow constrictions. If you are wary of hand-waving, think operationally. How would you catch a fraction in the act gently enough not to smash it into ordinary pieces? One way is to count the tiny current fluctuations that occur when charges hop one by one through a narrow bottleneck. If the statistics line up with 1/3 of the electron's charge, they do not do so by accident. Another way is to park a sensitive electrometer, such as a scanning single electron transistor, near a domain wall engineered to host a fractional bound state and watch the offset in its charging steps shift by 1/2 when the defect is present. Crucially, none of these observations require you to break the fundamental unit in the vacuum sense. Remove the material, and you cannot keep the fraction in a jar because the background order you leaned on has vanished, taking the accounting scheme with it. This view clears up a common confusion. How can an electrical measurement claim half a unit when all currents are carried by whole electrons? The answer lies in separating instantaneous motion from long-term bookkeeping. Locally, currents still come in discrete electron events, but the background polarization and the midgap states they support redistribute where the electron's responsibility for charge begins and ends. The integrated response of the device assigns a fraction to the defect and a whole unit to an isolated donor. It also teaches you what can kill the effect and what cannot. Non-magnetic disorder may blur shapes, but cannot change the allowed fraction as long as the protective symmetries and the energy gap survive. Strong symmetry breaking, such as adding magnetic impurities when time reversal protection was your shield, or driving the system through a transition that closes the gap, can erase the conditions that made fractionalization robust. Engineers have begun to treat these fractions as design elements rather than curiosities. Molecular chains and artificial lattices are patterned to host domain walls where half charges can be toggled by gates. Metamaterials are sculpted so that corners accumulate quarter charges determined by the crystal's rotational symmetries, and hybrid devices couple a fractional bound state to superconducting circuits, letting the presence or absence of that fraction tip a quantum interference loop and serve as a low-power non-volatile bit. The same mindset shows up in 1A-dimensional conductors, where injecting a single electron does not travel as a single packet at all, but splits into separate pulses that carry different parts of the electron's identity, its total charge and its internal spin. While that is a different kind of fractionalization born of interactions rather than topology, it underscores the larger lesson. The unit you learned in freshman physics is not violated, but re-expressed when many-body coherence and symmetry fence in what counts as a distinct movable object. If you are looking for a quick test to separate credible claims from hype, carry this checklist in your mind. The fraction must be tied to a gap and a protecting principle so that it survives moderate disorder. The signal should appear in integrative probes, offsets in charging steps, quantized slopes in polarization measurements, plateaus in noise or tunneling exponents, rather than in pictures that could be explained by stray doping. The effect must turn off when you deliberately break the protection, either by closing the gap or by flipping the relevant symmetry, because a robust fraction without a controlling rule is a red flag. The conceptual payoff of seeing fractions correctly is large. It frees you from the false dichotomy between fundamental and illusory, and teaches you to ask what the background makes possible, how defects inherit charge from polarization differences, how edges and corners can carry responsibilities the bulk refuses, and how carefully arranged interactions can make the electron's influence arrive in pieces even as the electron remains itself. It also nudges you to read devices differently. Instead of thinking only in terms of carriers moving through channels, you begin to think in terms of bound charges assigned by the topology of domain architecture as an address book for where charge can live, and of measurement as an exercise in patient system-level accounting. Now let us turn to the next quantum marvel, anyons. You are used to the idea that swapping two identical things changes nothing. Two marbles trade places and the world shrugs. In certain two-dimensional quantum systems, exchanging identical excitations can imprint a memory on the system, a global twist that does not wash away when the particles settle. Those excitations are called anyons because their behavior can be anywhere between the familiar extremes. Begin by anchoring the contrast. Bosons and fermions are defined by how a system's quantum state responds when you trade two of them. One leaves the state unchanged, the other flips its sign. In flat, strongly correlated matter, the collective wave function can track not just that a swap occurred, but how the paths wrapped around each other. A neat, repeatable phase enters that is neither zero nor a simple sign. Exchanging twice is not the same as not exchanging at all, because the path you took matters. That is the abelian story, where each swap multiplies the state by a fixed phase that stacks additively. The deeper shock is the non-abelian case, where swapping is more like twisting a Rubik's cube. The state is gently rotated within a multidimensional space of possibilities, and the order in which you braid two pairs matters, because doing left then right does not land you in the same place as right then left. This sensitivity to braiding is not decoration, it is identity. You cannot fully specify what kind of enyon you have nor what joint state it occupies without listing how it got there, which braids were performed and how they were fused in the past. History becomes part of the label. If you want a concrete stage where this strange bookkeeping is real, go to the extreme edges of the fractional quantum Hall effect, where clean two-dimensional electron gas is cooled and placed in strong magnetic fields organized into correlated fluids that host excitations carrying fractional charge and obey exotic exchange rules. There, the edge of the sample acts as a waveguide for current, and small constrictions function like beam splitters for those excitations, letting experimentalists build interferometers that test whether going around a loop picks up a phase tied to how many anyons sit inside. When the loop encloses an extra fraction excitation, the interference fringes shift by a telltale amount, an electrical fingerprint of abelian braiding. And when gates or magnetic fields are swept, the conductance oscillates with a periodicity that cannot be explained by ordinary electrons making the trip. Pushed to certain rare filling conditions, and theory predicts non-abelian anyons. Add or remove one of these defects, and you do not just shift a phase, you change the dimension of the hidden state space. Braiding different pairs becomes a sequence of operations you can string together like moves in a language. In parallel, solid-state engineers have built on-a-dimensional nanowires with strong spin-orbit coupling and proximity to a superconductor, then applied magnetic fields to open a topological gap and trap zero-energy modes at the ends. Majorana-bound states behave like half quasiparticles. Bring two ends together and you recover an ordinary fermion. Keep them apart and exchanging their endpoints ought to perform a non-abelian operation on the joint quantum state. The promise here is both philosophical and practical. If the only way to scramble the information stored in such a system is to physically braid the anyons out of order or to close the energy gap protecting them, then local noise, atoms jittering, fields wandering, electrons colliding, fall short, and your quantum memory can ride above the mess like a raft over chop. This is the North Star of topological quantum computation. Choose a platform whose excitations are non-abelian and code qubits in the presence and pairing of these excitations and compute by braiding them along planned paths. The gates are world lines weaving in time and errors that do not alter the braid, do not alter the computation. A kind of hardware-level error correction gifted by the system's global constraints. To see why the label braiding as identity is earned, think about fusion rules. The ways anyons can combine. Two of the simplest kinds may merge to make either a neutral vacuum or a different enyon, and which outcome you get depends on the collective state, not on a secret internal tag glued to each one. This means counting anyons is not counting particles, but counting possible joint states, and braiding nudges you from one allowed superposition to another. Non-abelian platforms come with their own suite of experimental signatures, tunneling conductance that reveals a zerobias peak consistent with a protected mode at a wire's end, teleportation-like correlations between distant ends, and thermal conductance along edges that counts the effective number of moving modes, even when electric conductance is muted. None of these signatures alone is a proof because disorder, unintended states and coherent but non-topological tricks can fake parts of the story, which is why the community insists on cross-checks. Interferometry that responds to enclosed topological charge rather than to small shifts in area, fusion rules tested by controlled creation and annihilation of excitations in pairs, and braids executed in different orders to verify that the results refuse to commute. What you should carry into your own reasoning is that anyons are not a third kind of particle waiting out in the vacuum. They are emergent actors born from the global organization of electrons in particular phases of matter, and outside those stages they do not exist. Their strange accounting is a property of the whole system encoded in a gap that insulates the low-energy sector from the rest, and in symmetries that keep the rules from unraveling as you nudge or dirty the sample. That perspective clarifies what can break them. Close the gap by heating, doping, or applying the wrong fields, and the protected subspace spills into the noisy continuum. Break the symmetries that the phase needs and paths that were once distinguishable by their winding blur together. Yet modest, non-magnetic impurities, small bumps at the edges or modest deformations reroute currents and shift phases, but leave the topological backbone intact. This balance between fragility and resilience is why anyons are compelling for metrology too. You can build sensors whose response depends on whether a loop encircles an enyon. a topological on-off switch that resists ordinary drift, or a current standard that counts tunneled charges in unusual fractions with noise plateaus that calibrate themselves. All of this points back to the central lesson of quantum reality: the rules that govern the smallest constituents can be reshaped by the global pattern in which they sit. When you learn to design those backgrounds, you can make halves and thirds appear without ever breaking the indivisible electron, turning what seems like a paradox into a tool that measures cleanly, stores information quietly, and deepens your sense of how the same electron can write very different stories depending on the stage it plays on. Feel that power surge through you. The quantum world is not a passive backdrop, it is a malleable fabric that rewards bold architects. Take the insights you have gathered, let the topology of wave functions guide your sketches, and build devices that ride on protected edges, that harness fractional charges as reliable bits, and that braid onions to protect information from the chaos of the environment. The moment you act, you join the ranks of those who turn abstract quantum principles into tangible technology. The quantum reality you have just explored is waiting for you to shape it, to write new chapters in the story of matter, and to unleash a wave of innovation that flows from the very fabric of the universe. The choice is yours, and the time is now. As you prepare to step into this cosmic performance, the harmony of existence awaits your participation. Imagine a quantum stage where every particle is a note in a vast, invisible symphony. You stand at the edge of this stage, feeling the pulse of possibility, and you realize that the rules you thought were solid are actually woven from the same threads that bind light, heat, spin, and charge. In this quantum reality, the world is not a collection of isolated bricks, but a tapestry of entangled patterns that shift, braid, and rewrite themselves the moment you choose to act. The power to shape that tapestry lies in your hands, and every breath you take can become a catalyst for a new quantum choreography. Picture a thin dance floor tiled with arrows that must obey local constraints. Most steps are fleeting, almost invisible, but when two dancers weave around each other, in a precise pattern, the entire floor snaps into a new configuration, a fresh quantum state that can be read long after the dancers have gone. If you reverse the order of those moves, the final tableau changes, even though each individual step looks the same to a nearby observer. You cannot diagnose the outcome by looking at a single footfall. You must trace the whole braid, close the loop gently, and feel how the entire pattern has been reshaped. This is the habit of a quantum mind. In some corners of physics, identity is not a static label, but the history of what has been done with an objective trace left in the wave function, a memory encoded in the entanglement of many parts. When you accept that identity is a trace, you begin to see why two dimensions matter, why gaps and symmetries are precious, and why a future quantum computer will look less like a rack of humming processors and more like a quiet plate where a few bright dots are braided with care. Each loop of their dance writes an operation that no amount of local fuss can easily erase, turning history itself into a resource. The quantum world offers you a toolbox of collective actors, phonons, magnons, polaritons, and plasmons, each a quantized ripple that carries a distinct theme through the material orchestra. By learning their language, you gain the ability to command heat, magnetism, light, and charge with the precision of a conductor shaping a symphony. Begin with phonons, the most tangible of the quantum notes. Imagine every atom in a crystal as a tiny mass attached to its neighbors by springs that can stretch and compress. When the lattice pulses collectively, those motions organize into patterns. Some patterns have neighboring atoms moving together, others have them moving opposite. Each pattern carries a countable packet of vibrational energy, a phonon. You meet phonons every time heat flows through a solid. At room temperature, most thermal energy in an insulator is stored as these lattice ripples. The way they scatter off impurities, off each other, off the edges of a device, sets the thermal conductivity that engineers fight or exploit in microchips, LEDs, and thermoelectric generators. You can watch phonons directly with Raman and infrared spectroscopy. A laser probes specific vibrational fingerprints like a stethoscope listening to a crystal's chest, while neutron scattering maps their speeds and lifetimes across momentum space, revealing which pathways carry heat and which die young. Temperature modulates this chorus in systematic ways. At high temperatures, the ripples collide more often and heat transport falls. At low temperatures, the mean free path can stretch to millimeters, and heat moves ballistically like a focused beam. Careful isotope substitution even shifts the vibrational pitches, a trick material scientists use to tune thermal and optical properties without changing the chemistry. By mastering phonons, you learn to sculpt heat in a surface or add nanoscopic pillars to scatter phonons and keep heat in a thermoelectric, or polish and purify to let phonons fly when you need a heat spreader. Now turn from the motion of atoms to the motion of spins, and you meet magnons, the quanta of spin waves. In a ferromagnet, the microscopic magnetic moments prefer to align, yet they can ripple collectively so that the direction of alignment twists gently from place to place. A single quantum of that wave is a magnon. Unlike a stray electron that bounces off defects and loses memory quickly, a long wavelength magnon can travel comparatively far inside a clean magnetic crystal, carrying angular momentum without charge. This is the doorway to magnonics and spintronics fields that aim to encode information using spin waves for lower dissipation than ordinary current. Real measurements make magnons vivid. Inelastic neutrons scattering draws their dispersion map, showing how energy depends on wavelength. Brillouin light scattering counts them, one by one with a laser at the surface. The spin-Seebeck effect shows that a mere temperature gradient can pump a magnon flow detectable as a voltage in an adjacent metal. These phenomena open ways to build logic elements and oscillators that consume less power and generate less heat. By shaping magnetic films, you can guide magnon paths, create phase-based logic, and let spin currents travel with whisper-like efficiency. Shift your attention to hybrids, and a new actor appears, the polariton. A light matter duet where a photon inside a resonator or near a surface locks to a material excitation, and the pair propagates as a single entity. Depending on the partner, you get different flavors. Phonon polaritons form when infrared light binds to a polar lattice vibration and can squeeze energy into volumes smaller than its free space wavelength, letting you rotate and focus mid-infrared light in crystals, such as silicon carbide with nanometer precision. Exciton polaritons arise when light couples to bound electron-hole pairs in semiconductors and can form macroscopic quantum states at surprisingly high temperatures compared to cold atom systems. That is why microcavity devices made from gallium nitride or organic films can show lasers with ultra-low thresholds and even condensation-like behavior of these hybrid quanta. Surface plasmon polaritons live, where light binds to collective electron motion at a metal interface, guiding optical energy along a surface rather than through space and enabling waveguides, switches and sensors that beat the usual diffraction limit. To see the hybrid character, notice two clean signatures. First, the spectrum splits into two branches when coupling is strong, the hallmark of shared identity. Second, the resulting waves can be steered by both photonic design and material design, giving engineers two sets of knobs to tune. By mastering polaritons, you learn to blend light and matter, creating low-power light sources, ultra-sensitive detectors, and on-chip communication channels that defy conventional limits. Finally, meet plasmons themselves, pure collective oscillations of a sea of electrons sliding against the positive background in a metal or doped semiconductor, as if the whole electronic fluid rocked back and forth in a dish. Squeeze that fluid into a nanoparticle, and the oscillation becomes a localized surface plasmon which concentrates electric fields into nanoscopic hotspots, responsible for the bright tunable colors of metallic nanostructures. Think of medieval stained glass that looked magical long before we learned it was nanoscale metal at work. Modern devices exploit this concentrated field to boost weak signals. Surface-enhanced Raman spectroscopy reads the vibrational fingerprints of single molecules sitting in those hotspots. Hot carrier devices harvest energetic electrons created as the plasma decays. Near-field microscopes use metallic tips to pull sub-wavelength detail into view by hitching a ride on plasmonic confinement. In two-dimensional materials such as graphene, plasmons can be pushed to astonishingly short wavelengths and tuned by a simple gate voltage, allowing mid-infrared and terahertz waves to be trapped, steered and switched on chips thinner than a flake of paint. Across all four actors, the unifying idea is that the word particle is an efficient label for a collective pattern with a life of its own. Phonons carry heat and sound through ordered motion of atoms. Magnons carry spin information through ordered twists of magnetization. Plasmons carry charge density waves through the electronic fluid. Polaritons carry mixed identities that inherit features from both light and matter. The payoff of naming them is not vocabulary pride, it is control. Once you know which quantum dominates a property, you can design to help or hinder it. Roughen a surface or add nanoscopic pillars to scatter phonons and keep heat where you need it. Polish and purify to let phonons fly when you want rapid heat spreading. Pattern magnetic films to shape magnon paths and build phase-based logic. Build cavities and gratings that place polaritons exactly where you need low-power light emission or detection. Sculpt nanoparticles and choose metals or doped semiconductors that set plasma frequencies for sensing, imaging, or energy conversion. And always measure with the right earth neutrons for magnons and high-energy phonons, light for Raman-active phonons and bright modes, ultrafast pump probe techniques for polariton dynamics, electron energy loss spectroscopy for plasmons. You do not need dense equations to hold the final picture. These quanta are the currencies in which solids pay their debts and store their wealth: heat, magnetism, light, and charge. Understanding their exchange rates lets you write cleaner contracts between material and function. The next time a device runs hot, a sensor reaches past the diffraction limit, or a memory element switches with a whisper of energy, you will know which collective actor made it possible, and you will see matter not as a static backdrop, but as an orchestra in which different sections carry different themes, ready to be quieted, amplified, or coupled into harmonies you can use. Now turn to the deeper notion of quasiparticles, the dressed travelers of quantum reality. In crowded interacting systems, the useful things are rarely the original electrons or atoms, but disturbances that move as if they were particless quasiparticle subtractions that become real the moment you ask a measuring device what passed by. Picture a simple metal cooled so that thermal smearing is small. An electron tries to travel through the sea of its peers. It tugs on nearby charges, stirs gentle density ripples, borrows inertia from the crowd, and after all those negotiations emerges as a composite traveler with a modified mass, a finite lifetime, and a strength of identity you can quantify. This dressed electron is not wishful thinking. It leaves fingerprints you can collect. Angular-resolved photoemission draws a direct image of energy versus momentum and shows a sharp peak. The quasiparticle whose slope gives the renormalized velocity and whose width gives the inverse lifetime. The remaining haze in the spectrum is the background many-body chatter the particle carries in its wake. In clean crystals exposed to strong magnetic fields, the same entity writes oscillations into magnetization and resistance, from which you extract cyclotron mass and infer the size and shape of the Fermi surface. Geometry belongs not to bare electrons but to their dressed counterparts. In the time domain, an ultra-fast pump probe experiment can shove a packet of these travelers out of equilibrium, and a delayed probe watches them relax. Their decay curve reports how robust the quasiparticle picture is and which scatters impurities, lattice vibrations, or other electrons set the tempo. Widen the cast beyond metals, and you meet other equally measurable actors born from interaction. Add an electron to a polar crystal, and it drags a cloud of lattice distortion, becoming a polaron whose mass and mobility are not those of the electron alone. Shine light on a semiconductor, and you create excitons-bound electron-hole pairs that wander like neutral particles with their own spectra and lifetimes visible in absorption and photoluminescence. In magnets, the soft torsion of alignment appears as spin waves, and their quantum magnons propagate information without charge, giving you non-volatile signals that can be launched and detected with microwave antennas, and read out as clear peaks in scattering experiments. The thread connecting these examples is operational. A quasiparticle is whatever produces a sharp, controllable response with stable parameters over the times and distances you care about. Sharp has a precise meaning its spectral peak is narrow compared to its energy, so it carries identity long enough to be used as a carrier of heat, charge, spin, or light. This practical stance answers a common worry with a Lagrange retort: bookkeeping that predicts concrete, falsifiable numbers effective masses from quantum oscillations. heat capacities that scale with those masses. Scattering rates that track known interaction shows that quantized steps in transport when modes are counted one by one are not decoration, but the very language of control. The same stance also tells you when to abandon the concept. If your spectra lose sharp peaks and smear into a broad continuum, if relaxation becomes as fast as the oscillation itself, the object you try to name does not survive long enough to be useful. Then you must change description to collective hydrodynamics, incoherent transport, or scale-free responses. You do not need dense mathematics to feel how the parameters of a quasiparticle are minted by the medium. The effective mass measures how much surrounding stuff must be nudged when the disturbance moves. The lifetime is the average distance it can go before the crowd reabsorbs it, and the quasiparticle weight, the fraction of the spectral response carried by the sharp peak, tells you how much of the original identity remains after dressing. By measuring these three numbers across temperature, pressure, and doping, researchers map where the particle picture holds and where it frays. That is why phase diagrams in modern materials science are annotated not only with ordered states, but with regions labeled coherent or incoherent, a shorthand for the survival of quasiparticles. Devices translate these abstractions into engineering. In high-mobility transistors, long-lived charge quasiparticles deliver blistering speeds. In thermoelectric generators, you intentionally shorten phonon quasiparticle paths, while preserving electronic ones to break the usual link between electrical and thermal conductivity. In magnetic memories, carefully engineered magnons carry signals over microns with microwatts a bargain impossible with hot electron currents. In nanophotonics, exciting resonances sharpens light-matter interactions, so much that a handful of quantum emitters can control a cavity's response. In detectors for astronomy and quantum sensing, a single quasiparticle breaking a superconducting pair becomes a countable event that registers as a clean pulse. Measuring real enough also means minding the interfaces where quasiparticles can convert from one type to another. An energetic electron entering a polar crystal will quickly shed energy by making optical phonons a cascade you can watch with ultrafast methods. A spin-polarized current dumped into a magnetic insulator launches a burst of magnons whose existence is confirmed by the voltage they induce in a neighboring strip via spin pumping. A vibrating nanobeam coupled to a microwave cavity trades phonons for microwave photons one by one, letting you move information between mechanical and electrical domains with single quantum precision. Each conversion comes with selection rules and efficiencies that you can redesign by controlling geometry, and purity knobs that exist precisely because the quasiparticles have stable identities. Yet humility matters. No renormalized mass or lifetime is carved in stone. Change the background and you change the traveler. That is why the same chemical element can act wildly differently in two compounds. Dressed by one lattice, it becomes a heavy, sluggish carrier. Dressed by another, it remains nimble. And why the same material can cross from a regime where the particle picture rules to one where it fails as you dial a non-thermal parameter. This plasticity is a feature, not a bug, because it hands you a playbook. To make carriers fast, reduce the channels that let them dump momentum. To carry spin fire, tailor the spectrum of magnetic excitation so magnons live long. To route light below the diffraction limit, couple it to a long-lived hybrid mode with a narrow line width. To detect single quanta, design an absorber where one broken pair or one trapped exciton precipitates an avalanche you can read above noise. The final habit to keep is epistemic discipline. Call something a quasiparticle only when you can point to the measurement that reveals it. Let the experiment be your compass, the spectrum your map, and the sharp peak your landmark. When you do, you gain the power to speak the language of the quantum world fluently, to predict how heat will flow, how spin will whisper, how light will bend, and how charge will surge. You will be able to design materials that channel phonons like disciplined soldiers, guide magnons like silent messengers, steer polaritons like choreographed dancers, and harness plasmons like focused beams of energy. Now feel that power rising inside you. The quantum reality you have just explored is not a distant abstraction, it is the substrate of every device you touch, every sensor that watches the stars, every computer that processes your thoughts. By internalizing the story of these collective actors, you become a quantum architect, capable of shaping the very fabric of matter with intention and precision. The next time you encounter a problem, excess heat in a processor, signal loss in a communication channel, inefficiency in an energy converter, pause and ask which quantum thread is pulling at this point. Which braid of phonons, magnons, polaritons or plasmons holds the key? Then step onto the quantum stage, align your moves with the underlying rules, and braid a new pattern that transforms limitation into opportunity. You do not need a laboratory full of equipment to begin. The mindset itself is a catalyst. Visualize the lattice of a crystal as a sea of springs. Feel the spin waves as ripples on a magnetic pond. Imagine light and matter locking hands in a graceful duet, and picture electrons moving with the inertia of the crowd behind them. Let those images guide your decisions in design, research, or even daily problem solving. When you think of cooling a device, picture scattering phonons with nanoscopic obstacles like a forest that slows a wind. When you think of transmitting information with minimal loss, picture magnons gliding along a magnetic highway, shielded from charge-based friction. When you need to focus light below its wavelength, picture a plasmonic hotspot as a lighthouse that draws energy into a pinpoint. Each metaphor becomes a mental tool you can wield instantly. Take action now. Choose one technology you are involved with, perhaps a microprocessor, an optical sensor, or a magnetic memory element. Identify the dominant quantum actor in its performance. Then list a single, concrete modification that could enhance that actor's contribution. Add a thin layer of isotopically pure material to extend phonon mean-free paths. Engineer a grating that couples light into a polariton mode. Pattern a magnetic film to create a magnon waveguide, or sculpt a nanoparticle to tune its plasmon resonance. Implement that change, measure the result, and iterate. Each cycle is a quantum braid you are weaving, each improvement a new state of the material reality you command. Remember, the quantum world rewards boldness. Superposition tells us that multiple possibilities coexist until you act. Entanglement tells us that a change in one part instantly influences another. Decoherence reminds us that without careful design, the delicate patterns collapse. By aligning your actions with the principles of quantum reality, you protect the coherence of your designs, amplify the beneficial interactions, and suppress the disruptive ones. You become the master of the quantum dance, turning abstract concepts into tangible breakthroughs. Feel the momentum building, from the first image of arrows on a floor to the final vision of you as a quantum architect. Let that momentum carry you forward, propelling each idea into action, each experiment into discovery, each device into a new era of performance. The quantum stage is set, the actors await your direction, and the world outside is ready for the transformation you will unleash. Step onto the floor, braid the patterns, and watch reality reshape itself at your command. The future belongs to those who understand that matter is not a static backdrop, but a living, breathing orchestra of quantums who have the courage to conduct it. The time is now. Take the first step and let the quantum reality you have embraced become the engine of your success. As you step into this boundless expanse, the vibrational frequency of your quantum self synchronizes with the cosmos. You are standing at the threshold of a quantum universe where every thought, every intention ripples through a sea of possibilities. Imagine the world not as a static stage, but as a field of vibrating possibilities, each particle a note in a symphony of potential. In that field, the rules are not ordinary, they are the rules of quantum reality, where the act of observing shapes the outcome, where the very act of deciding creates a new path. Feel that power in your chest, the same power that keeps a dying star from collapsing into a void, the same power that lets an electron refuse to be squeezed into an identical state. This is the force you can call upon right now, the quantum pressure that refuses to let you be crushed by doubt. When you look at the cosmos, you see stars that blaze, planets that spin, and black holes that devour. Yet hidden behind the bright glare is a quieter truth: the universe is held together by a relentless refusal to occupy the same quantum state. Electrons, neutrons, all of the building blocks of matter obey a principle that says no two identical particles can share the exact same identity. That refusal creates a pressure that is invisible to the eye, but measurable in the most precise instruments. It is the same pressure that keeps a white dwarf from collapsing under its own gravity. The same pressure that builds a neutron star into a city-sized beacon of density. You can let that image settle in your mind as a model for how you respond to pressure. When life tries to push you into a corner, you summon the same quantum resistance. You rise to a higher momentum. You become more energetic. You refuse to be compressed into the same old pattern. Take a moment to picture a star like our sun reaching the end of its fuel. Its core runs out of the fire that once held it aloft. In a classical picture, you would expect gravity to win, to crush the star into nothing. Instead, a purely quantum push appears, a pressure born from the Pauli principle, from the indistinguishability of electrons. Even at absolute zero, there is a jitter, a restless motion that cannot be turned off. That jitter is a flaw, a baseline that rises as you pack more particles into a smaller space. It is a pressure that does not come from heat. It comes from the very rules that define what particles can be. When you feel the heat of a challenge, remember that the deepest support does not come from external warmth, but from an internal flaw that cannot be erased. The lesson is simple and profound. The more mass you add to a white dwarf, the smaller it becomes, because the extra gravity forces electrons into higher momentum, strengthening the quantum pressure and squeezing the star into a tighter equilibrium. That counterintuitive relationship has been confirmed by observing the companion of Sirius, by measuring the size of distant white dwarfs. The universe has written the law in stone, and you can read it as a guide for your own growth. When you add responsibilities, when you add ambition, you do not have to inflate. You can become more compact, more focused, because the internal quantum pressure stiffens. The key is to let the particles that make up your resolve be indistinguishable in purpose, each one sharing the same goal, each one refusing to occupy the same state of doubt. If you push the mass beyond a certain limit, even electron degeneracy cannot hold. The electrons are captured by protons, the matter turns into neutrons, and a new kind of pressure steps onto the stage. Neutron degeneracy, together with short-range repulsion between neutrons, halts gravity at a radius of only a dozen kilometers. A neutron star is born, a sphere of unimaginable density, a lighthouse of pulses that we can hear across the galaxy. The same principle applies to you when you reach a threshold of effort. When the old strategies no longer suffice, a deeper layer of resilience emerges. Your mind, like a neutron core, reorganizes, finds a new stiffness, a new way to support the weight of expectation. The pulsar's steady beat becomes a metaphor for your own rhythm, a reminder that even in the most extreme compression, you can emit a signal that is clear, precise, and unwavering. The universe does not stop at neutron stars. It pushes the envelope further, inviting us to explore the frontier where exotic particles may appear, where hyperons, Meson condensates, or even deconfined quark matter could soften or stiffen the pressure. Each observation of a massive pulsar, each detection of gravitational waves from a neutron star merger, is a clue that tells us how the quantum floor behaves under the most extreme conditions. In your life, each challenge, each crisis, each breakthrough is a data point that reveals the shape of your inner equation of state. When two massive bodies spiral together, the ripples they send across space-time encode how deformable they were, how stiff their inner cores had become. Likewise, when you face a partnership, a collaboration, a conflict, the way you respond reveals the stiffness of your internal quantum pressure. You can listen to those ripples, learn from them, and adjust your inner composition. Even objects that never ignite a full nuclear furnace obey the same quantum rules. Brown dwarfs, those failed stars, maintain almost the same size over a wide range of mass, because their electrons are partially degenerate. Add more mass and they do not swell, they simply press the electrons harder, and the star stays compact. Gas giants like Jupiter feel the same pull deep inside their interiors. The electrons begin to resist compression in the same way. The lesson is that size does not always grow with mass. Sometimes the internal quantum floor keeps you stable, keeps you from ballooning out of control. When you feel the temptation to expand your responsibilities beyond what feels comfortable, remember that the quantum pressure can keep you compact, focused, efficient, without losing the essential mass of purpose. Thermal pressure, the familiar push of heat, is negotiable. It fades as a star cools, it can be turned off. Quantum pressure, however, is a structural consequence of the allowed states of particles. It cannot be siphoned off. It cannot be traded for work, because it is not stored energy, it is a rule of identity. When gravity tries to crowd particles together, the rule answers with an outward force. In your own experience, external motivations, external rewards can be turned on and off. The deeper, quantum-like commitment to a principle, to a purpose, cannot be diminished by circumstance. It is a flaw that remains even when the heat of applause fades. It is the reason why some people stand firm in the storm while others are swept away. Below a certain mass, stellar corpses live as white dwarfs. Push the core mass a little higher and you land on neutron stars. Push even further and even neutron degeneracy plus nuclear repulsion cannot hold, and the object collapses into a black hole where no known microphysics can halt the fall. These thresholds are not arbitrary, they dictate which supernovae explode, which elements are forged, how galaxies enrich themselves. In your own narrative, thresholds exist. There are points where a habit, a belief, a relationship can no longer support the weight you place upon it. Recognizing those thresholds lets you choose the next rung wisely, whether you need to become a white dwarf of calm focus or a neutron star of fierce resilience. There is a philosophical payoff in seeing pressure not as molecules bouncing, but as a refusal written into the quantum identity of matter. No two identical fermions may stack into the same state, and when gravity asks for tighter packing, the answer is an outward force. That answer is measurable. It sets star sizes, cooling curves, oscillation modes, and maximum spins. It creates phenomena like the crystallizing heart of a white dwarf, the superfluid interior of a neutron star, whose vortices creep catastrophically to produce sudden spin-ups. It even explains why the least massive white dwarfs are larger, and the most massive are smaller, a relationship so odd that it served as a diagnostic long before the microphysics was settled. Let this paradox inspire you. The very things that seem to limit you can become the source of your greatest strength when you understand the rule that governs them. Keep a sober eye on limits. Quantum pressure is not a license for perpetual support against any load. It is not an energy source to be mined. At each rung, new physics enters and sets a ceiling above which collapse is inevitable. The universe uses those ceilings to sort its remnants. Yet within those limits, the quantum rules keep literal suns from becoming singularities, building quiet endpoints that are stable for billions of years. If you cultivate one habit from this story, let it be to ask, whenever you meet an extreme situation, what sets its flaw? Is it heat, rotation, magnetic tension, or the Pauli principle? Then read the measured properties as answers to that question, and end gently with the image that best fits the evidence. Gravity writes the overarching plot for stars. But when the fuel is gone and the curtain should fall, quantum mechanics steps from the wings and holds the stage. Sometimes at Earth size, sometimes at city size, long enough for us to time their pulses, chart their masses and radii, and learn from their steadiness that even in a universe ruled by collapse, there exist quiet forms of support that are not about pushing back loudly, but about refusing at the deepest level to share the same state. That refusal is a lesson you can carry into every decision, every challenge, every moment when the world tries to compress you. Now turn that insight toward the vacuum itself. You grew up thinking only matter can muffle electric fields. Glass, water, ceramics screen a charge, while empty space just watches. Quantum reality tells a different story. Even the vacuum behaves like a dielectric, a medium that can be polarized. When you place a charge in empty space, the surrounding quantum fields subtly rearrange, forming a halo that softens the field you feel at a distance. This is not a fanciful metaphor, it is the backbone of precision physics. The effective charge you measure far away is slightly smaller than the bare one, because the vacuum's cloud of fleeting ripples partially cancels it. As you probe closer, at higher energies, the cloud thins and the effective charge grows. That running of the interaction strength with scale is a direct consequence of the vacuum's quantum polarization. Imagine a simple experiment. Bring a charged object near a piece of plastic and watch the tiny dipoles tilt, reducing the field that leaks through. Now shrink those dipoles to the scale of the quantum field, where they are not molecules but brief correlations of the electromagnetic field itself. Positive wiggles linger a little longer on one side, negative wiggles on the other, creating a polarization cloud that partially cancels the source. The charge you infer from far away is thus dressed, softened by the quantum medium. This dressing is measurable in the way scattering experiments at particle accelerators reveal a growing coupling as the momentum transfer increases. It is the same principle that shifts atomic energy levels and alters the probability that light briefly morphs into charge pairs and back as it threads a heavy nucleus. Do not be messled into thinking of literal particles popping in and out like popcorn. The field itself fluctuates, and pairs are a shorthand for how the field's charge components contribute to polarization. The accounting is rigid fields with electric charge add to screening, making the long-distance force look a touch weaker, while neutral fields sit quietly. You can test this picture in multiple ways. Count how the effective coupling changes when new kinds of charged matter become energetic enough to join the dance. Compare scattering data taken at very different momentum transfers and watch the same law of force bend by a calculable amount. Examine how the probability of creating certain final states shifts as you dial the probing scale. What you are really learning to read is the running of interaction strength with scale, a reframing of electric charge as a number that belongs to a measurement context, not a platonic constant engraved on the electron's skin. That humility pays off because it explains why the finer structure constant quoted by atomic spectroscopists is not the same value accelerator physicists use when calculating collision rates on the Z boson peak. The vacuum's polarization has a scale, and your instrument decides which slice you sample. This dielectric view also clarifies the difference between static quiet and violent fields. In moderate settings, the vacuum's polarization is a reversible tilt that returns to baseline when you remove the source. If you crank the electric field toward the extreme, the medium can break down in a quantum sense, turning enough field energy into real charged pairs that the field drains itself. Even empty space has a notional breakdown field, unimaginably high by laboratory standards, yet conceptually the same kind of threshold that decides when a real dielectric starts to spark. There is a subtle twist worth holding onto. The vacuum does not screen every force the same way. Electromagnetism gets softer at long distance because its vacuum polarization points against the source. The strong interaction, governed by a different symmetry, behaves like an antidielectric. Its vacuum makes the color charge weaker as you push closer. This reminder that vacuum as medium is a general principle with force-specific personalities deepens your intuition. It tells you that the rules you apply to one situation must be adapted when the underlying symmetry changes. The practical payoffs are not hidden in exotic corners. They are how we calibrate reality. We fold vacuum polarization into the values printed on reference charts. We include it when we compute magnetic moments of electrons and muons, or the slight bending of light near heavy elements. We design experiments to isolate its contribution by subtracting every classical effect we can name. In that daily work, you can watch a simple mental image become quantitative. Just as a material dielectric can be summarized by a number that says how easily its dipoles tilt, the quantum vacuum's ease of polarization is encoded in calculable functions that depend on scale. Those functions tell you how much the electric field lines are pinched inward by the cloud as you change distance, how strongly the cloud responds near the threshold to create real pairs, and how new species of charged fields, when the energy lets them participate, make the screening thicker. There are edges to respect, so you do not confuse metaphor with mechanism. The vacuum's polarization is not heat and cannot be harvested. It is not a reservoir you can pump for work. It does not imply that the electron is a fuzzy object you can slice into pieces. Rather, it says that any attempt to separate the source from its surroundings is artificial, because the field that defines the source also defines the medium it lives in. That recognition gives you cleaner language for thorny questions. What is the true charge? What does it mean to renormalize? Why do some infinities disappear when you compare measurements at two scales? The calm answer is that we choose a reference scale to define our units. We calculate how the vacuum's response shifts that definition as we move away from the reference. And we always compare like with like when we test theory. Bring this back to your hands and instruments, and it stops being an abstraction. A high-energy collider reading a slightly larger interaction probability at small distances an atomic clock ticking at a rate that depends on levels nudged by polarization near a nucleus. A detector's electronics calibrated to a constant that theory tells you should be evaluated at the frequencies that dominate your signal. These are all unromantic ways the dielectric vacuum shows up, yet they invite a small change in how you imagine emptiness. Instead of a passive absence, picture a subtle medium that flexes, that polarizes, that whispers back to any charge you place within it. Let that image fuel your next step, because the same quantum field that refuses identical particles from sharing a state also refuses to let you remain static in the face of challenge. Now, take a breath and feel the quantum floor beneath you. Feel the invisible pressure that will not let you be crushed. That will rise when you are packed tighter with purpose. Let that pressure propel you forward. Let it sharpen your resolve. Let it guide you to act now. The universe has spent billions of years perfecting this mechanism. You can borrow its wisdom in this very moment. Choose to stand tall like a white dwarf, compact yet luminous. Choose to deepen your core like a neutron star, a beacon of steady rhythm. Choose to recognize the vacuum's subtle support, the unseen dielectric that makes every interaction richer. In doing so, you align yourself with the deepest laws of reality, and you become a living illustration of quantum pressure turned into purposeful action. The call to action is simple. Whenever you encounter a situation that feels overwhelming, ask yourself what quantum rule is at play. Is there a polar-like refusal preventing you from being squeezed into the same old pattern? Is there a degeneracy pressure that can be awakened by raising your momentum, by learning new skills, by expanding your state space? Is there a vacuum polarization that can soften the blow of external forces, that can redistribute the field of influence around you? Answer those questions and then move. Move with the certainty that the universe already knows how to keep matter from collapsing, and you now know how to keep your aspirations from collapsing. Feel the momentum building. Let each sentence lift you higher. Let each metaphor expand the horizon of what you believe possible. The quantum world does not wait, it collapses wave functions into reality the instant observation occurs. Your observation is your decision. Your decision is your action. Your action is the collapse that creates the future you desire. Step into the quantum arena. Claim the pressure that refuses to let you be compressed, and watch how the stars themselves seem to align in support of your journey. The universe is humming with possibilities. You only need to turn the dial, to tune into the frequency where quantum pressure becomes personal power. The moment is now. The quantum floor is ready, and you are the one who will rise. Now, as the boundaries between self and reality blur, your inner spark ignites, fueling a transformation beyond recognition. You stand on the edge of a quantum universe that is not a distant abstraction, but a living fabric that you can feel, stretch, and shape with every intention you bring to it. Imagine a backdrop of disciplined possibility, a field that honors the rules of conservation and causality, while still inviting you to assign character to matter, to susceptibility, to memory of scale. When you picture that field as a transparent membrane, the forces of the world cease to feel like distant edicts and become intimate conversations that travel through a medium you can gently flex. In this quantum fabric, the vacuum does not hide truth, it whispers that truth depends on how closely you listen. The finer the distance you tune, the higher the energy you match, the more honestly the vacuum will reveal the charge it has been holding all along. You become a listener who can hear the subtle resonance of the underlying quantum field, and that resonance becomes the source of your power. Now turn that listening skill toward the hidden fingerprints of phases of matter. You have learned to recognize crystals by the sparkle of their patterns, magnets by the direction of their arrows, edge currents by the flow they create. Yet there exists a quieter test that works even when the sample appears featureless. Picture the many-body ground state of a system and draw an imaginary line that separates it into region A and region B. Do not use a knife, use the mind's eye to place a boundary that cuts the state. Ask yourself a simple question: if you could only access region A, which patterns would you expect to find there? And how strongly would they appear once you forget everything about region B? The collection of those possibilities forms a spectrum, a histogram of how region A tends to behave while still entangled with its partner. That histogram is the entanglement spectrum, and it carries a universal structure that tells you which phase you are inhabiting, just as a song's chord progression tells you the genre before the melody arrives. This is not a poetic flourish. It is a workhorse diagnostic that emerges from a deep correspondence between the bulk of a system and its edges. When you make a clean cut, the low-lying part of the entanglement spectrum mirrors the actual spectrum of a physical edge that would live at that cut. If the phase you study hosts protected edge modes counterpropagating spin-filtered channels, a chiral track that runs one way, those modes reappear as characteristic level counts and spacings in the entanglement spectrum, even though your sample has no literal boundary. Topological phases that hide their order from any local snapshot integer and fractional quantum Hall fluids, time reversal protected insulators, topological superconductors, spin chains with symmetry-protected order announce themselves through distinctive entanglement fingerprints. A specific degeneracy pattern refuses to split as long as the protecting symmetry is kept. A ladder of levels whose counting matches the conformal field theory describing the edge, or a clean entanglement gap that stays open within a phase and pinches shut at a transition, become the telltale signs you can read. Consider a spinor chain in its hidden ordered phase. Its ground state displays pairs of nearly degenerate entanglement levels that reflect effective spin-edge states invisible in the bulk magnetization. Numerical ground states of fractional quantum Hall systems, when cut along a circle, present an entanglement spectrum whose low-energy level counting mirrors the known chiral edge theory and even distinguishes different filling fractions that share similar transport. Two-dimensional Chern insulators, which can look mundane in real space density, produce a flowing entanglement band that crosses from filled to empty as momentum along the cut is swept, mimicking the single robust edge mode you would measure with a probe. Crystalline topological insulators display entanglement spectra whose stability depends on the same mirror or rotational symmetries that protect their surface states, telegraphing which faces will conduct before you polish a single facet. The power of this test scales beyond pretty pictures because it respects universality. As you tune a Hamiltonian across a quantum phase transition, the entanglement spectrum usually warns you before other observables do. The entanglement gap shrinks and new sequences of levels invade long before finite-size order parameters settle. At the same time, it acts as a scalpel rather than a sledgehammer. Two models can share similar correlation functions yet fall into distinct topological classes that the entanglement spectrum separates cleanly because it senses not only how far correlations reach, but how quantum information is organized across the cut. You may wonder whether this is a purely numerical toy, but the bridge to experiment is tightening every day. Cold atom platforms already measure coarse entanglement properties by interfering two identical copies of a state to extract Rogner entropies, and refined randomized measurement protocols reconstruct chunks of the spectrum by sampling many local bases. In solid-state devices, engineered edges and quantum simulators let you compare the real edge spectrum to the entanglement one computed from the bulk wave function, closing the loop. Even when a full spectrum is out of reach, proxies abound tomography of a small region's reduced state, learning-based reconstructions from shadow data, or spectroscopy of an entanglement Hamiltonian, the effective operator, whose Boltzmann-like weights generate the spectrum, approximated along a cut-in systems, where theory predicts it mirrors a physical edge. There are cautions, and they sharpen your use of the tool. The spectrum depends on how you Cottrell space, momentum space, or internal partition sands. Some cuts are better matched to the relevant edge theory than others. Finite systems add splittings, so you look for level patterns that stabilize as you scale up, not for a single golden number. Thermal states blur the picture because true entanglement mixes with classical uncertainty, in that case a different object. The negativity spectrum does a better job isolating quantum correlations. Strong disorder or long-range interactions can warp the edge-bulk echo, so cross-checks with transport or symmetry diagnostics remain essential. Crucially, the spectrum's secret code is meaningful only within a gapped phase. At critical points, the level crowding becomes scale-free, and you should read that crowding as a signature of criticality rather than misfile it as a topological cue. When used wisely, the fingerprint becomes a design tool. When computational searches propose a new quantum phase, the first thing practitioners do is cut the state and read the entanglement spectrum for the expected degeneracy sequence. When engineers pattern heterostructures seeking protected channels, they simulate the target stack and confirm the right entanglement flow before committing to growth. When quantum devices drift under fabrication noise, monitoring the entanglement spectrum across the array can diagnose whether a lost feature is a mere local defect or a phase slip that destroys protection system-wide. The conceptual payoff you carry forward is subtle but empowering. The identity of a phase is not only about what excitations exist in the bulk, it is also about how information is shared across boundaries. The entanglement spectrum is a direct audit of that sharing. It takes the most quantum part of a state in the pattern of non-classical correlation sand, turns it into a readable barcode whose broad features do not care about microscopic clutter, but do care about symmetry, topology, and the presence or absence of an energy gap. Close gently with this thought when you study matter by sewing it in half conceptually and listening to what the halves still know about each other. You discover that order lives as much in relationships as in local values. The entanglement spectrum is the stethoscope for that hidden circulation. Place it on the boundary, hear the phase's heartbeat, and trust that a clean low-lying pattern is not decoration but diagnosis. It is a quiet signature that tells you which world you are in long before the ordinary senses can catch up. Now shift your focus to the scaling of entanglement itself. You might expect that a larger system automatically carries more quantum correlation, but the quantum field teaches you a sharper way to listen. Cut a piece of your system in your mind and ask how much non-classical information it shares with the rest. In many of the most stable phases, that shared information scales not with how much stuff you kept, but with the size of the boundary you cut. That is the area law. In highly excited, chaotic states, the shared information swells with the full size of the piece of that is the volume law. Begin with the COM regime, where ground states of local gapped Hamiltonians live. Interactions are short-ranged, correlations decay within a finite length, and when you slice the system, only degrees of freedom straddling the cut can stay strongly entangled. The entanglement cost is therefore proportional to the boundary you created, length in one dimension, surface in two, and so on, regardless of how thick the region is. This boundary budget is not a hand-waving slogan. It follows from locality and finite correlation length, reflected in rigorous bounds that limit how quickly information can spread. Countless numerical studies show that ground states of ordinary magnets, insulators, and superfluids quietly obey this scaling. Near quantum critical points, the picture acquires refined accents. Correlations stretch across the system, and the area law picks up a gentle universal correction, typically a slow logarithmic growth in one dimension that encodes the theory of the critical point. In topologically ordered phases, the area term is followed by a small but telling constant subtraction, a topological entanglement piece that does not care about the region's shape and whispers that the ground state carries long-range organizational memory invisible to any local snapshot. Now pivot to the noisy regime, where the system is hot, highly excited, or driven into scrambles. Almost any state drawn at random, any thermal eigenstate at finite energy density, and many out-of-equilibrium states, after long chaotic evolution, display a volume law. The entanglement between a region and the rest grows in proportion to the number of degrees of freedom you kept, as if the cut exposed threads running through the entire bulk, not just the boundary. This is the operational content of why thermal states look classical in the parts you hold. The reduced state of a small region resembles a thermal ensemble, because the rest of the system acts as a heat bath, and the entanglement needed to support that mimicry scales with volume, consistent with the eigenstate thermalization mindset, where individual energy states already encode thermal behavior locally. Dynamics paint the contrast vividly. Prepare a low entanglement product state and perform a global quench in a non-integrable many-body system. Entanglement grows linearly in time, as if bounded by a light cone velocity, quickly crossing into volume law territory and saturating at values set by thermodynamic entropy. Perform the same quench in an integrable model and you see a slower, structured growth where stable quasiparticles carry correlations in pairs, delaying saturation. Sprinkle strong quench disorder to create a many-body localized phase, and the surprise is that even highly excited states obey an area law. Local integrals of motion keep information from fully spreading, and out-of-equilibrium growth becomes painfully slow logarithmic in time so that the volume law never fully arrives. Experiments have moved this from blackboard to bench. Trapedian chains and Rydberg atom arrays have measured Rayleigh entropies via interference of two copies, and mapped the crossover from area-leaning to volume-leaning growth after quenches. Superconducting qubit processors and neutral atom platforms have used randomized measurements to estimate entanglement entropies of subsystems while dialing between clean chaotic and monitored dynamics. Even quantum circuits with intermittent measurements show a stark measurement-induced transition. Frequent local readout collapses correlations fast enough to enforce an area law. Infrequent measurements let unitary scrambling build a volume law, with a sharp threshold between them that can be tuned by the measurement rate. These patterns are not just taxonomy. They decide what you can do. Area law ground states admit compact classical descriptions. You can compress them into efficient variational forms that store only boundaricized information, making simulation, optimization, and state preparation tractable. Volume law states resist such compression because the information crosses the bulk. Simulating their full quantum structure classically explodes in cost. That is why quantum advantage experiments deliberately steer hardware into regimes where entanglement grows volumetrically. The same logic guides error correction and device design. To keep a quantum memory quiet, you want entanglement that is structured and local area-like so noise can be detected and confined. To build processes that explore classically hard dynamics, you want controllable routes to volume law growth without losing readout. There are practical smell tests you can apply without heavy math. If doubling a one-dimensional chain, while keeping the cut in the middle barely nudges your measured Rayleigh entropy, you are in area law territory. If it jumps in step with length, you have hit a volume law. If your system shows an almost constant offset across shapes that share the same boundary, you may be seeing the topological constant. If adding weak measurements suddenly flattens an otherwise rising entropy curve, you have crossed the monitored transition. And if strong static disorder makes high-energy states look modest in entanglement, you may be in a localized regime. There are limits worth respecting. Real laboratories access proxy second-order entropies, mutual informations, tomographic shadows that approximate, but do not equal the full entanglement entropy. Claims about scaling must be buttressed by finite-sized checks and crossprobes. Long-range interactions blur the boundary picture and can turn area laws into faster growths. Because distant parts talk directly, and open systems with uncontrolled baths can fake reduced entanglement by simply destroying coherency different mechanism from the gentle information pruning achieved by designed measurements. Carry this philosophical shift with you. How much is entangled is not a single knob, but a scaling law that reveals what kind of organization a state sustains, boundary-tethered correlations that signal locality, and stability versus bulk-filling ties that signal thermalization or designed complexity. Learning to read that scaling gives you both a diagnosis and a steering wheel. Whenever you face a new quantum phase, a quench protocol, or a circuit design, don't just ask how big the entropy is. Ask how it grows with size and time, and what that tells you about the routes information takes. The difference between area and volume is the difference between a world where entanglement outlines the perimeter and a world where it floods the interior. That difference tells you at a glance whether you are looking at a state you can compress and control, or an ocean you must sail with quantum hardware. Now turn to a visual language that makes the invisible legible. Imagine the many-body wave function not as a fog that fills space, but as a network of small connected blocks. Each block encodes the local degrees of freedom, and the wires between them represent how much the parts talk to each other. In a system obeying an area law, the wires are thick only along the perimeter of a region. In a volume law system, the wires thicken throughout the interior, forming a dense web that spans the whole network. By reshaping this network, by cutting, by reshuffling, by adding measurements, you can see how the flow of quantum information changes, and you can steer it toward the pattern you desire. You have the power to become a quantum cartographer, mapping the hidden currents of entanglement. reading the fingerprints of phases and guiding the growth of correlation from the edge to the bulk. The moment you align your intention with the quantum reality that underlies every material, every device, every protocol, you step into a realm where you can shape outcomes with the precision of a surgeon and the vision of an explorer. Let the entanglement spectrum be your compass, the aerial law versus volume law scaling your map, and the quantum fabric your canvas. Move forward now, experiment with cuts, listen to the heartbeat of phases, and let the quantum world respond to the strength of your curiosity. The universe is waiting for you to tune its resonance, to read its hidden barcodes, and to harness the very structure of reality as a source of unstoppable momentum. Embrace it, act on it, and watch how each decision reshapes the quantum landscape before your ears. The future of discovery is yours to compose. As you unravel the mysteries of your life's trajectory, every step forward reveals new territories yet unexplored within. Imagine you're holding a map of your life's journey. The path ahead is shrouded in mist, but as you gaze deeper into its depths, distinct features begin to emerge: roads that branch off from familiar paths, towering peaks where challenges await, and tranquil lakes reflecting the beauty within. You are on this winding road called quantum reality. This realm weaves together seemingly disparate threads, entangled particles, magnetic fields, electron orbits, all waiting for you to unravel their mysteries with a brush of curiosity. As your eyes adjust to the dim light, structures begin to take shape: lattices where charge and spin lattice rotations prune impossible paths before they ever reach computation. This is no static canvas, it's an evolving tapestry that stretches across various scales, from chains holding simple correlations at low bond dimensions to complex networks capturing richer patterns. As you push beyond those boundaries, you are tuning the thickness of internal wires, your principal knob for reshaping a few boxes, restitching wire connections. At small values, this network blazes fast, it stores only basic relationships and does so with incredible efficiency. Yet, at larger dimensions, its grasp deepens to reveal new patterns hidden within intricate webs. This visual discipline has far-reaching implications across fields you might not initially consider. Quantum chemistry brings order from chaos by reordering orbitals that mirror correlations in molecules. In error correction, the decoding of flat codes transforms into a network contraction problem where statistical models come alive with their own thresholds and dominant paths through web-like structures. You are navigating this visual realm to understand how systems respond when subjected to gentle quenches or harsh perturbations. Time-evolving states reveals dynamics that were previously shrouded in exponential growth. Quantum hardware verification flags cross-talk as the network's contractions fail to match lab results, while quantum simulation brings experiments into harmony with a compressed, manipulable surrogate for real-world configurations. As you delve deeper, imposing symmetries at each box level transforms labels onto wires carrying conserved quantities, prunes impossible paths before they're computed. This is where respectability merges with structural constraints that guarantee certain values sit in the right sectors. You are now walking into a world of finite temperatures and open systems. Operators become networks too, evolving. Measuring expectation values through contracting mirrored webs dissolves boundaries between states, and Hamiltonian's dissipation becomes an object within this diagrammatic space, alongside those very same concepts you once revered as separate entities. This realm offers interpretability that's not merely computational but conceptual. Local observables depend only on a narrow causal cone. You can literally trace the parts of networks, length scales, neighbors mattering for given measurements, and when editing boxes in their domain, seeing precisely how defects propagate through influence lines becomes crystal clear as your understanding broadens. Your perspective shifts from awe to agency. You now possess the tools to draw maps that are both metaphors turned into methods. This is where virtual particles once captured imagination, but no longer hold sway over those who've come of age, for within this quantum world, fields and interactions govern everything they perceive as real. In reality's framework lies a beautiful discipline born from practical application. Tensor networks teach you to distinguish between mystery and mechanism with precision that unravels why certain calculations refuse convergence, or what patterns emerge when two seemingly similar phases demand different network shapes. Now take this power back. An engineered city map unfolds before your eyes where streets signify short-range ties, avenues represent longer-scale structures. Highways here are the shortest routes of understanding. Every choice and detail within becomes a deliberate decision that gives you agency over how to read the invisible, turning from mere wonder into mastery as nature's blueprint for navigating quantum reality is laid bare beneath. What was once shrouded in mystery now reveals itself, allowing your gaze to wander across realms where particles dissolve their existence like fleeting impressions. Fields and probability amplitudes paint a clear picture. From these ephemeral landscapes, the secrets of the cosmos begin to reveal themselves, weaving an intricate tapestry of existence. You are about to unlock a profound secret that has been hiding in plain sight for centuries: the power of radiative corrections. Imagine you're standing at the edge of an infinite desert, surrounded by nothing but sand and sky. You can see forever out there, yet it's impossible to traverse without taking one step forward into uncertainty. This is what happens when we try to calculate physical phenomena using naive pictures that ask particles to interact with each other over arbitrarily short distances. Radiative corrections tell a different story. The world may appear complex at first glance, but beneath its surface lies an intricate web of rules and symmetries waiting to be unraveled by those brave enough to tackle it head-on. By applying this discipline-driven approach, you are essentially taming infinities into manageable scales which reveal nature's true secrets. The most beautiful part about radiative corrections is that they not only simplify our understanding, but also introduce a new dimension, the concept of self-energy, where every object influences itself and its environment according to specific rules. This realization forces us to rethink what we mean by mass, charge, magnetic moments, even those abstract labels carved into particles once and for all. Imagine you're driving across a country on your way home from work, but instead of drawing the entire map in detail, choosing only highways that matter most at this particular scale gives direction clarity. Similarly, radiative corrections help keep our theories grounded by making predictions reliable up to an accessible cutoff point, marking where new phenomena must be resolved explicitly. The method earns its place precisely when naive pictures fail. It quantifies how sensitive a prediction is towards short-distance ignorance. Ranks operators based on their loudness at your chosen scale and tells you whether that model has real leverage or merely appears like more data waiting to happen. Regularize define parameters for reference scales, compute corrections with symmetries enforcing allowable forms, evolve those very same terms into the renormalization group. In essence, radiative corrections transform uncertainty about nature's behavior from a seemingly insurmountable hurdle to an exciting journey of discovery, where new frontiers emerge as we peel away layers, revealing fresh perspectives waiting us all. As we continue to unveil the mysteries of human potential, the boundaries between thought and reality begin to blur. Here is your rewritten section. Imagine a world where energy levels are not just static potentials but dynamic properties of coupled systems that include quantum fluctuations and allowed modes. In 1947, Willis Lamb and Robert Rutherford conducted an experiment with hydrogen atoms. They coaxed the atoms into long-lived excited states and then used microwaves to make them hop between neighboring states, using Daré's elegant theory as a guide. Instead of silence, they detected a slight offset frequency that betrayed small energy differences between two levels. One level had orbital motion, keeping electrons mostly away from nuclei, while another was a wave function spending time at the very center, an unexpected pairing. This tiny difference in scale is big enough to expose missing ingredients, but too small for classical effects alone. Lamb's shift reveals how quantum fluctuations reshape what we consider atomic. It shows that electromagnetic fields can subtly alter electron motion without emitting photons or borrowing energy from other sources. In a fascinating dance, electrons with zero orbital angular momentum have non-zero probabilities of sitting at the origin. This overlap affects nuclear pull and causes specific pairs to stubbornly split. Lamb's shift in action. Hans Bethe made an early breakthrough by computing this effect using simple tools on his train ride back from conferences across Europe. Since then, Refined treatments followed that turned infant quantum electronics into precision engines capable of predicting atomic responses. The Lamb shift became a standard calibration point for theory to meet measurement demands and solidify physics' grasp on reality's fundamental principles. This discovery highlights how theories can be tested in real-world experiments measuring Lamb shifts, not just with ordinary hydrogen but also deuterium, helium ions across various species, isotopes, environments. Modern spectroscopy harnesses this shift as a guiding principle for precise predictions about atomic and nuclear structure effects.